בוקר טוב, בוקר טוב לכולם, בואו תתיישבו. שומעים אותי בסוף? רונית, את שומעת? לא? טוב, בוקר טוב לכולם. בואו תתיישבו כולם כדי שנוכל להתחיל. אוקיי, בוקר טוב. סטארי, שב. טוב, אני ממש שמח לפתוח את יום העיון הזה, ויש עוד כל מיני אנשים שדיווחו שהם בפקקים, אז עוד הצטרפו, אבל אני באמת שמח לפתוח את יום העיון הזה, ויש לזה כמה סיבות, תכף נגיע למוטי, אבל חוץ מזה שאנחנו באמת במין עידן פוסט קורונה, והרבה זמן לא היו ימי עיון, הייתה איזו אפיזודה קצרה של כנס החברה הגיאולוגית, אבל חוץ מזה כמעט אין מפגשים בפורום הזה, אז זה דבר ראשון שמשמח. והסיבה המרכזית כמובן שמביאה אותנו לכאן בשמחה, היא יום העיון לרגל החגיגות ה-70 לילד הזה. ובאמת דבר מרגש. אז היום יום העיון הוא אמנם חגיגת יום הולדת, אבל הוא יום עיון מדעי בתחום הגיאוכימיה, והיום הזה, ההרצאות היום יזכרו בעצם, יעברו דרך ההיסטוריה המדעית של מוטי, החל מעבודות על גיאוכימיה של המעטפת, אל הופמן, שגם ליווה, היה שותף של מוטי בשנים הראשונות, רונית אחר כך הסטודנטית הראשונה, אחר כך נתקדם לדבר על אגמים, יש איזה אגם מפורסם שמוטי עבד עליו, מי תהום, אוקיינוסים, שינוי אקלים, ויוחנן קושניר מלמונט יסיים בהרצאה על שינוי אקלים בהולוקן ובעתיד. אז אנחנו בעצם עושים רצף ארוך של סקירה של גיאוכימיה בכלל, ובמקרה הגיאוכימיה הזאת גם חופפת את ההיסטוריה של מוטי. אז אני מניח שכל האנשים היום יגידו, אני יודע גם שחלק יראו דברים אישיים ועל הקשר שלהם למוטי. מוטי גם בשבילי הוא כמובן מנטור וקולגה וחבר. אני בעצם התחלתי איתו מסמינריון בשנה ג' ומאז אנחנו ביחד. אז אני מאוד שמח שאנחנו כאן בסיטואציה הזאת. ולמדתי המון דברים ממנו, אבל אז אם אני רק בוחר את אחד מהם, אני זוכר שפעם הוא סיפר לי שכשהוא מגיע לתת הרצאה, הוא מגיע כל פעם עם אותו סט של שקופיות, מטעין את ה-USB, מרים את העיניים לקהל ומחליט על מה הוא ידבר. אז תמיד ההרצאות שלו מאוד מלהיבות ויפות, ואז אני רק הבאתי שקופית אחת, שקופית של... כן. רואים יותר טוב עכשיו? זאת שקופית של מוטי שיוני גולדשמיט צילם לפני בערך חודש בים המלח. מוטי כאן שוכב על סלע שהוא בעצם סטרומטוליט, הוא סוג של עצה שגדלה לאורך חופי ים המלח, ואחד הדברים באמת המיוחדים אצל מוטי זה הקולגיאליות שלו, העובדה שהוא תומך בתלמידים בעיקר, גם בקולגות וחברים לפני הקלעים ובעיקר מאחורי הקלעים, ורואים את זה, ואני מניח שנשמע על זה במשך היום, אבל פה אני רוצה רק להראות שזו דוגמה לחוסר קולגיאליות, כי הסטרומטוליט הזה כבר נכבש פעם, ואני לא יודע מי יודע מי זה הבחור פה מצד שמאל? בני בגין, כן, איפשהו בתחילת שנות ה-70, אבל יושב בדיוק על אותו סטרומטוליט, אתה ידעת את זה?
כן, אני צלצלתי אליו באותו ערב, ואמרתי לו, תגיד בני, הסטרומטוליט שלו מצולם פה, ואיפה הוא נמצא? כי הייתי בטוח כל השנים שצילמו את צילם בנחל דרגה, ואז הוא אמר לי נחל נור, אבל יש לנו עוד כמה תמונות, גם יהודה לא שוכב שם, אנחנו תפסנו את החזקה של בני בגין.
כן, אז אוקיי, אז זאת סגירת מעגל יפה, התחלנו בתחילת שנות ה-70 עם הסטרומטוליטים והגענו עד הלום. אז זהו, אז אני שמח לפתוח את יום העיון, ואני מתכבד להזמין את ישו קולודני, שיגיד גם הוא כמה מילים. ישו.
אם תרצה זה כאן זה עובד, אם תרצה זה עובד כאן, אתה יכול לדבר.
בוקר טוב. סוף העולם. בשכונה שבה אני גדלתי בבת גלים, דיברו תמיד בהערכה על אלה שיעני עשו בגרות. אחר כך כולם עשו בגרות. בשלב מאוחר יותר אמרו מי עוד בקיבוץ? כולם עזבו את הקיבוץ. אחר כך כולם למדו באוניברסיטה. עבר זמן, כולם עשו דוקטורט. היום כל אחד בן 70. סוף העולם, והעולם שותק. אצלי מוטי ילד. תלמיד שנה א' במחזור, נדמה לי מהמחזור שאחרי מלחמת יום כיפור. אחר כך המאסטר של מוטי שהדרכתי יחד עם סטארי בתחילת שנות ה-80 על גיאוכימיה של אורניום, שאת זה עשינו בשיטה מאוד יפה. אני לא יודע כמה עוד היום אם מוטי בקורס שלו מלמד על שיטת עקבות ביקוע או לא, אבל לדעתי זאת שיטה סופר אלגנטית, אינטלקטואלית היא סופר אלגנטית, ומוטי בשיטה הזאת מיפה תכולת אורניום בפוספורית שלנו, במיקרו, ומצבי חמצון של אורניום בפוספורית. מאחורי זה יש סיפור פוליטי מעניין, פעם אפשר לספר אותו. אחר כך כאילו הדרכתי את מוטי בדוקטורט שלו. איזה הדרכתי, מי הדרכתי? יפה שקראתי אותו בקפדנות, קראתי את כל פרק והערתי, אבל מי שהדריך אותו זה היה על הופמן, ומוטי בעצמו הדריך את עצמו. משם יצא מומו, שעל זה תשמעו היום. בהמשך, מוטי מגלה באמת את האוצר שעמיתי ואני כבר גילינו קודם, את צורת הלשון, ומזה גם צומחת העבודה שמוטי ואני הדרכנו ביחד את מלכה מחלוס, ואחר כך מזה צומח הקידוח בים המלח, ומשם צומחות המון עבודות של מוטי ושל חברים שלו. אמרתי סוף העולם, כשעושים חגיגה כזאת למישהו, לצבי גרפונקל, לעמיתי ולי, לסטארי, מי עורך אותה? מוטי שטיין. אבל עכשיו עולות בדעתי כמה מהחברים שלי יודעים שדברים שעולים בדעתי לא תמיד יש להם הקשר הגיוני. אבל מה שעולה בדעתי זה השורות של אלתרמן. כמעט תמיד עולה בדעתי שורה של אלתרמן. שכתב על הפלמ"ח, מה נשיר עליהם, מה נשיר? הם עושים את זה יפה מאיתנו. בעצמם הם כותבים להם, ואפילו ספרים כבר נתנו. זהו טיב הפלמ"ח, הוא איננו משאיר כל מלאכה לשלו משלנו. במידה רבה מוטי כזה. מוטי לא מארגן את יום העיון הזה, מה נעשה? איך נסתדר? בלית ברירה, עדי ויעל, בסגנון שמקובל היום על ראשי ממשלה ועל ראשי אופוזיציה, נכנסו מתחת לאלונקה, וארגנו לנו את יום העיון הזה. על זה אנחנו כולנו מודים להם. בשמחתו של מוטי כולנו שמחים כמובן, ותזכרו, אלה רק 70 השנים הראשונות. חכו למה שיגיע. כל לחיים מוטי, שפע ברכות.
תודה רבה.
תודה אישי. אוקיי, אז תודה לישו. אני רוצה להזמין את זוהר גבירצמן, שישא דברים בשם המכון הגיאולוגי.
בוקר טוב. אני רוצה לברך את מוטי בשם המכון הגיאולוגי והעובדים שלו על שירות של כמעט 20 שנה, אם אני זוכר נכון. הגענו ביחד כמה ימים, חודש, למכון הגיאולוגי, ומוטי במשך השנים האלה הטביע חותם עמוק על המחקר במכון הגיאולוגי ולכל היושבים פה, על המחקר במקום הזה, במכון למדעי כדור הארץ ועוד מקומות. אבל לא על המחקר אני אדבר, זה עוד מעט יעשו אחרים יותר טוב ממני. אני רוצה להציג את מוטי מהמבט האישי שלי. אנחנו לכאורה באים, לא לכאורה, אנחנו באים מדיסציפלינות אחרות. לא גדלנו באותה חבורה, לא כרונולוגית, לא מבחינת תחומי העיסוק. אבל אולי אתה לא יודע, יש בינינו משהו משותף, ואני תמיד הסתכלתי עליך כסוג של אח בוגר. אני נתקלתי בעבודה שלך כשצבי הדריך אותי, והסתכלנו על הגיאותרמה של משטר החום בליטוספירה, בעבודה שלך, ומבחינתי היה לי איזשהו 10 שנים הפרש בינינו אצל צבי, והסתכלתי עליך כאיזה סוג של מודל. לא בכל דבר אתה מודל עבורי, אבל בשני דברים שמאוד חשובים לך ולי, אתה כן הבאת בשבילי מודל, ואני חושב שכשאני חושב שני אבות טיפוס, מה זה מדען ומה זה גיאולוג, אז מוטי הוא מודל טוב להרבה מהיושבים פה. כשאני חושב מי הוא מדען, אז אני מדמיין את מוטי, זה שילוב של איזה סוג של אינדיאנה ג'ונס, לפעמים, ולפעמים, אם אתם זוכרים בשנות ה-70 טלוויזיה חינוכית, דוקטור האפבקט, לא יודע מי זוכר את זה, וקשה לעמוד בפני המבט של מוטי, השיער הפזור, המבט החודר, משדרים סקרנות, חוכמה, דמיון, חזון. השיחה איתו תמיד שולפת איזה שילוב של אנליטיקן ואינטגרטור, איש של סינתזה ואנליזה, בו זמנית, שואל שאלות, מתווה דרכים לחקור אותם, מדען. כשאני חושב מי הוא גיאולוג, אני גם חושב על מוטי. כמה מהיושבים פה שולטים, אני כמעט אולי אגזים ואומר, בכל ענפי הגיאולוגיה, או בכל כך ענפים מהמדע הזה. גיאוכימיה של קרום ומעטפת וההשלכות הגיאודינמיות של זה, גיאוכימיה של גשם, מים, מי ים, מי אגמים, סדימנטולוגיה, סלי משקע, פטרולוגיה מגמטית, פלאוקריאונוגרפיה, פלאואקלים, שדה, מעבדה, ואפשר עוד להמשיך, אבל אני לא צריך להמשיך, עוד מעט תראו את זה. מוטי הוא יחיד במינו, אין ספק בכך. כיף לשוחח איתו, כבוד לברך אותו. מזל טוב מוטי.
תודה רבה. אני רוצה להגיד לזוהר, יש עוד שני דברים שמקשרים בינינו. אחד זה אבא שלך, שזכיתי באמת לדבר איתו, לשמוע אותו, אפילו כמעט לעשות משהו ביחד, אבל לא הספקנו לצערי הרב. זה היה, הוא הביא לי סדרה של שבלולים מסיני מורכר, ועד היום נשיא במדינה. תזכיר לי, אני חייב להשלים את זה מתישהו.
יש לך הרבה זמן, רק התחלת.
והשני זה, יש לך תלמיד שלך, איכשהו עכשיו אצלנו במשפחה, אז זה גם דבר נוסף.
תודה זו. טוב, אני רוצה להזמין את עודד שיארגן את המושב הקרוב. ועוד משהו, אני רוצה לבקש מכל הדוברים להשתמש במיקרופון, כנראה שמאחורה לא שומעים, אבל אף אחד לא אומר, אז זה לגבי זה. בואו נראה אם...
זה עובד, נכון?
זה עובד, כן. טוב, יש עוד 2 דקות עד ההפסקה, אז אולי מאוד דייקן, אבל אני אשאיר לך.
מה?
תכף, הנה.
Okay. So here is our first speaker for the day, Al Hoffman. I first heard about Al and his work when I was at Caltech, reading about diffusion and about chromatography, and he had very good papers on the subject. And at the time he was working at the Carnegie Institution of Washington. But then in 1980 he was called back to Germany to start the Max Planck Institute of Geochemistry, which Al succeeded to turn into a world-leading institution. And I think Al will correct me, but I think one of the best ways of achieving this goal was to collect many very good people that came to work with Al and to work at Mainz. And one of these persons was Moty Stein. And together, or I think that both Al and Moty, maybe Moty learned it from Al, maybe he had it before, as Yeshu said before, but both of them really try the best they can to go as high as possible and to look at the largest picture possible in order to understand the Earth. And they had together 2 Nature papers, 2 very famous papers, and it all started from xenoliths in Israeli basalts. Xenoliths are foreign rocks to all the lakes people that are here and do not know what it is. And but in the first paper they succeed to show how they can go from these xenoliths, from these few pieces of rocks, into the formation of the whole Arabian Shield, and the Pan-African. And later on, in the Momo paper, which is also here, they took it to the whole earth and the whole mantle, and I think this is a wonderful example. In recent years, after retiring, Al shared his time between Mainz in Germany and Lamont where he spends time with Steve Goldstein, another speaker of today. And today he will talk to us from Mainz. So, and many more. And today is your day. So Al, please, the stage is yours.
Well, thank you very much for inviting me. I'm really honored by this invitation. And I just want to say happy birthday, Moty. I'm a little embarrassed to have to give the first talk, but I just want to remind you, maybe most of you know this, but the name Momo it's the name of a little girl in Michael Ende's novel about this little girl who was fighting the old gray men who were stealing people's time. And she got back the time from these gray old men and gave it back to the people. But in the context of this here, the Momo means actually something different, namely major orogeny and mantle overturn. And the whole thing was entirely Moty's idea, but I think maybe I made up the name Momo, although Moty will have to correct me on that. My memory is not quite firm. But I'm a proud co-author of this paper, and I want to try to tell you how this relates to what we're doing today, because I think it's still very relevant. Here you see, it's Moty's most highly cited paper, and it was published in 1994, so it's a while ago. But I think what we then said is largely still true today. And I'll just read you the first line. Many hitherto puzzling features of the isotope and trace element geochemistry of the Earth's mantle and crust can be explained if Earth history is punctuated by episodes of enhanced exchange between lower and upper mantle. Okay, so this idea of episodic crustal growth, triggered perhaps by mantle plumes, then found its expression in this diagram. So there are thought to be periods of times that we call the Wilsonian periods, where you have normal plate tectonics, where there may be more or less separate convection schemes in the upper and lower mantle, and then they're interrupted by these Momo episodes when there is a large-scale exchange between these two reservoirs. I think there has been an accumulation of evidence in favor of this. One thing, for example, are the peaks in the zircon abundance as a function of age. Everybody has probably seen these diagrams, mostly made by Kent Condy as evidence for episodic continental growth. Interestingly enough, Condy, I think in recent years, has come around and has tried to actually explain away these valleys that between these peaks as times not of just crustal destruction rather than less crustal growth. But I think this is a bit far-fetched. Particularly, Parman recently wrote a paper showing just from sediment zircons from sediments of restricted ages, 500 million year periods. He showed that these valleys in the zircon abundances persist even if you look at time periods just immediately after one of these valleys. So if these valleys in the zircon abundance were caused simply by crustal destruction, during and just after that time, those zircons still should have been around, but they never existed. There's also very good evidence, at least from numerical convection models, that show a strongly episodic behavior in convection. For example, here is the melt production on the left, produced per year as a function of time, and you see that there are very strong peaks in melt production as in geological history. So actually convective systems like the Earth are normal to behave this way, not as a continuous machine that constantly produces continental crust and magmatic output, but intermittent. Now, this is the diagram where we try to explain the epsilon neodymium, the isotopic composition of neodymium as a function of age. And you see in the upper diagram, this is something that was known as PRIMA, that stands for prevalent mantle. For example, this is the Ontong Java plateau. So magmatic rocks, large-scale magmatic provinces through Earth history seem to fit on a single growth curve. And the important thing here is that this growth curve does not end up with an epsilon value like mid-ocean rich basalts, which would be between 8 and 10 here, and they don't remain on a primitive mantle composition where epsilon would be 0, but somewhere in between. And so what does that mean? So to repeat, this mantle, there seems to be a large mantle reservoir, which is not primitive, and it's not morgue-like, but it's somewhere in between. It's partly depleted. So recently, together with Steve Goldstein and a Connie Class, we've taken a stab at this problem, looking at an old mass balance approach, very simple, where you divide the Earth into 3 reservoirs: continental crust, depleted mantle, and underlined by a primitive mantle. And there are some equations that use the epsilon neodymium as a criterion for the degree of depletion. And you can calculate the mass fractions of this depleted reservoir, and you can calculate the concentrations of neodymium in this reservoir from that in a very simple mass balance calculation. And the kind of data that go into this, here's the epsilon values for mid-ocean rich basalts in blue, and contrasting with continental rocks, and the big yellow circle is the average continental composition by Roberta Rudnick's, for example. And some other continental rocks to show you that continental rocks are consistently low epsilon values, and oceanic rocks, and not only the mid-ocean rich basalts, but also ocean island basalts, shown here in purple, have high epsilon values, but the purple rocks are not as high as the blue rocks, the mid-ocean rich basalts, but they look like they're part of the same population. When you make that calculation, the mass of the depleted mantle that you get that way comes out to less than 30%, depending on what you assume for the epsilon value of the continental crust, which we don't know all that well because we don't know well what the lower continental crust is like. But it's less than 30%, so that it seems to fit well with the region of the mantle above the 660 kilometer discontinuity. Now, we did an alternative mass balance using a different criterion, namely the niobium-uranium ratio. I'm showing here why that's a useful criterion, namely mid-ocean rich basalts and OIB, ocean island basalts and plateaus, all share the same high niobium-uranium ratio, which is systematically higher than the primitive mantle, just like epsilon neodymium. And continental rocks, which are consistently low, niobium uranium. So we can do exactly the same mass balance that we did for the neodymium for using the niobium uranium. And when we do that, we get a different answer. Instead of less than 30%, which we had for the neodymium, we're getting somewhere, depending on the exact value of the uranium in the continental crust, we're getting something like between 60 and 80% of the mantle would be that depleted reservoir from which this is just morgue right now. But of course, if we use not the morgue composition, but some lower epsilon value, that mass balance shifts a little bit. And so if we shifted the epsilon value of that bulk reservoir, go back here for a second, the bulk reservoir of morgue and OIBs to somewhere between, let's say, 5 and 10, okay? So the total thing here is somewhere between there. We do that, we can calculate on the right-hand side the what kind of epsilon value you would need to get to 60 to 80%. And we see that even if the epsilon value were low as 5 or even 4, we don't get to the 60 to 80% mass fraction. So there's something fundamentally wrong with the whole mass balance that we do. We cannot reconcile these two mass balances. And so there's something wrong with the simple 3 reservoir model. Now, people may not be very surprised at that, but it has nevertheless been the basis for essentially all the current estimates of what the morgue source reservoir is composed of and how large it is. So we cannot reconcile these, so the simplest solution to this problem is to postulate a 4th hidden reservoir. Now, what might that be? We have a fanciful diagram for this. Maybe it formed very early in history, and it was maybe a primordial oceanic crust that was subducted, and perhaps because of its high iron content was dense enough, so it was subducted and stayed near the core mantle boundary, and because of its high density, it would simply stay down there and be out of sight and never be found again. So the remainder of the mantle then is changed its composition, and this would be the early enriched reservoir EER, and the complementary early depleted reservoir would be here, which would occupy essentially the rest of the mantle. And from that, if we then extract continental crust from this kind of mantle, we can get a residual mantle with the niobium, uranium 46, and so forth that we see. And but the question is, what is that early enriched reservoir? It might be primordial crust that I just outlined a little bit, or it might be caused by the fractionation and overturn of an early magma ocean, or it might even be lost to space lost by collisional erosion of that primordial crust. We don't know, we don't see it, and we don't know whether it's buried or lost to space. But it must have existed, and if we do that, I won't go into details here, but we can then reconcile the mass balances of both the niobium uranium here between, which would then shift up to 80 to almost 100% of that mantle, and the epsilon value that would be somewhere here. For example, if the morgue and OIB average for epsilon equal to 7, so somewhere between 5 and 8.5, which I showed before, that would also yield the same kind of answer between 60 and close to 100%. So by doing this, we can make the two mass balances agree with one another. If we then look at the kind of picture that we might get for the Earth evolution, and of course this is a very simplified thing, this early depleted reservoir is now no longer primitive, depleted, so it grows from epsilon 0 to epsilon, this is 4 here, the example I've chosen, but it might be somewhere between 3 and 5, we don't know, but roughly like this. And this would be differentiated into continental crust, which would be off the screen way down below, and the current mid-ocean rich basalts and ocean island basalt sources that would be formed by the residual mantle, which might be something like this. So this would have an average of epsilon of 6.5, for example. Okay, so you can make everything come out fine with this. And the question then is, what does it have to do with Momo? Well, it looks exactly like that's just what Momo is. You look at the diagram we made in 1994, which has an epsilon value of about 6. And you look at this image I just showed you, that also has, this happens to be like 6.5 here, and there's quite a bit of slop. We don't know the exact value, of course, neither do we know the exact value of this here at the time. But it may well be that this represents that bulk residual mantle that was formed after the early depleted reservoir differentiated itself into continental crust and a residual more plus ocean island basalt source result. So I think this may provide the explanation which we didn't really have in '94. This may provide the explanation for that Momo story that we had 25 years ago. This was, and this I would say that since this was Moti's idea completely, he just we were engaged in some loose conversation one day and shooting off all kinds of crazy stuff, and when he came with this, I latched onto this and I said, wait a minute, this is fantastic. Let's really work this out. And so it was Moti's idea, and I think he looks like a prophet here, and so I think that would be an appropriate description of that. So once again, Moti, best wishes and happy birthday, and we're all proud of you. Thank you very much.
Any question? Even Moti says, okay, I have a few, but I'll keep them for later. Or maybe I would ask one question. If these Momo events happen, this would be a good chance where you can sample the hidden reservoir, because you overturn the whole mantle. Can you see something special in these events that can give you a hint to the existence of a hidden reservoir?
Not really, because in fact, this is the stuff. The overturn does not show the hidden reservoir. It shows only what the depleted, early depleted mantle, not the enriched one, but the early depleted mantle reservoir did with itself by differentiating itself into continental crust and residual mantle of both Moor and ocean island basalts. So we're not, if we were seeing the early enriched reservoir, we would be using it up, and 4.5 billion years later, or whatever it was, it's still separate. Remember that this mass balance that we did here is not some kind of a terrestrial evolution. The mass balance is strictly present-day crust and present-day mantle. So there's no modeling involved in when continental crust was extracted. It's just a mass balance.
Okay. Thank you very much, Al, for joining us, and you're invited to stay and watch the rest. And but I'll invite our next speaker, Ronit Kessel, Ronit was a master student of Moti and me together, and worked, you wouldn't believe it, on real rocks and analyzed them, and was famous in the department for getting Amitai's permission to work alone on his ICP, which was something really extraordinary. And so we worked together. Later on, Ronit did a PhD with Ed Stolper on meteorites, and a postdoc in ETH in Zurich on the mantle. And in both of those studies, she went into the running experiments, and she built a wonderful lab, and a very impressive lab here in Israel. And I would invite Ronit to speak about her early reminiscence from the joint work that we did many times ago, and probably with some new understandings. So Ronit, please.
So happy birthday, Moti. I'm excited to be your first student. And thank you both, you and Oded, for introducing me to igneous petrology. So, אז אין לי, כן, רק, okay. So subduction zones are unique and complex environments where significant flux of material occurs between the mantle, the crust, and the atmosphere. Is it working? No? Good. Okay. So, and the agent of transfer of material changes as the process occurs. The subducting slab, the crust, the upper mantle, and the sediments on top of it all contain hydrous and carbonate phases. And with increasing pressure and temperature, these phases become unstable and break down, releasing water and CO2 fluids into the mantle wedge. These fluids are rich in incompatible elements, and they interact with the peridotitic mantle, metasomatize it, and eventually lead to its melting. And the melt erupts in volcanic arcs, releasing volatiles into the atmosphere. As subduction occurs and continues, volcanic arcs may amalgamate with one another and slowly create the continental crust. We can study subduction zones by simulating high pressure and high temperature, as I'm doing currently, and study the initiation of melting and metasomatism. But today I want to go back and revisit my master, studying the rocks exposed on the surface from the Pan-African orogeny as exposed in southern Israel during the last stages of the Arabian-Nubian Massif. So the continental crust in Israel was formed between 870 and 540 million years ago, and is exposed in Israel, in Timna, Amram, and Eilat. The major magmatic activity occurred between 650 and 600 million years ago, as huge amounts of granitic batholith and diorites into the newly forming continental crust, such as Elad granite. These rocks were studied by Ayelet Weissman, who was also a master student of Moti and Oded, and I will show some of her data as well. This stage ended with a regional uplift and erosion, and between 600 and 640 million years ago, a few swarms of dikes penetrated the rocks, as well as alkaline granites, such as Yehoshaphat granite. I focused on the dikes penetrating the rocks, and Amit Mushkin, also a student of Oded and Moti, studied the alkaline granites, the last stage of the Pan-African orogeny. So we found 3 generations of dikes. The oldest generation directing north-south, as we can see here, spanning a wide range of compositions from basaltic andesites to rhyolites, and they all contained hydrous phases such as amphiboles and micas. These dikes were cut by the second generation of dikes directing northeast-southwest. We can see them both here. Also spanning a very wide range of compositions from basalts to rhyolites, but they have no hydrous phases in them. And the last generation, the youngest generation of dikes, directing northwest, southeast, are basaltic dikes appearing only in Timna and Amram. So we have a few generations of, a few stages of magmatism, the dikes, the various swarms of dikes, and the alkaline granites, all very close in time and space, but they different in field relation, in petrography, as well as chemistry. We can place all the various rocks on a TAS diagram, a total alkali versus silica diagram, where we can see the different fields of the different rocks. And we can also subdivide this field to subalkaline rocks, meaning silica-saturated rocks, and alkaline rocks, silica undersaturated rocks. So the Eilat granites and the quartz diorite Amram all fall in the subalkaline field. The north-south dikes are also subalkaline, but very close to the boundary with the alkaline field. The northeast dikes are on the border, and the northwest dike is already in the alkaline field. And the alkaline granites, as well as mafic enclaves in them, are in the alkaline field. The subalkaline rocks are also subdivided to 2 subcategories by the iron to magnesium ratio, calc-alkaline and tholeitic rocks. And we can see that the Eilat granite, as well as the north-south dikes, are all calc-alkaline, where the northeast and northwest are tholeitic in nature. So we see in a very short time a transition of magmas from subalkaline, calc-alkaline rocks to tholeites to alkaline magmatism in a very short time in one place. We also see this transition from orogenic environment, a calc-alkaline environment, into an alkaline environment, which shows an anorogenic environment using trace elements. We see that the calc-alkaline rocks, the Eilat granite, falls in the I and S type granites, which are granites that were formed from melting of igneous or sedimentary rocks related to subduction zone activity. And the various dikes show a transition into an intraplate environment showing an A-type granites. I just want to mention that this graph is also only for the felsic rocks, so I don't show all the mafic rocks. And the alkaline rocks are also in the intraplate field, so we have a transition from orogenic activity to an anorogenic activity in a very short time. So all these dikes and alkaline rocks are very close, in a close association in time and space. So it points to a common evolution. And we want to study both the relationship between the different members in a given suite, as well as the relationship between the suites themselves. So first we start by evaluating the relationship of the various dikes in a given suite. If the different rocks were formed by different degrees of partial melting of a common mantle source, the initial melt will contain very high concentration of incompatible element that will go directly into the melt phase. And with increasing melt degrees, the concentration of the incompatible element will decrease, and only at high degrees of melting will the compatible element enter the melt. If the various rocks are related to one another by fractional crystallization from a given melt, then the initial melt will be characterized by very high content of compatible element, but this compatible element will directly go to the minerals crystallized, so its concentration decreases substantially, and only at the higher degrees of fractional crystallization will the melt have increasing concentration of an incompatible element. So we looked at two sets of relationships, thorium and niobium representing incompatible elements versus vanadium, which is a compatible element. The north-south dikes show a profile representing fractional crystallization. So the suggestion is that they were all formed by fractional crystallization of a given melt composition. Also the northeast and the northwest dikes, as well as the alkaline granites, all show relationships suggesting each group was formed by fractional crystallization of a given melt. However, we can see that the initial melt has different characteristics in terms of trace elements. So our suggestion was that all magma types were formed from a zoned lithospheric mantle. During subduction, when subduction was active, fluids penetrated the mantle wedge, carrying with them incompatible elements, and these elements entered and metasomatized the mantle according to their incompatibility. The fluids reached the hot zone where melting occurred. So if amphiboles were formed close to the contact between subducting sub and the mantle wedge, niobium entered the amphibole, and therefore niobium is enriched in the mantle only at the deep depth of the mantle, where thorium, uranium, and the REEs, which are highly incompatible, manage to reach higher distance and metasomatize the mantle at a shallower depth. When the subduction ended, this mantle wedge, chromatographically zoned mantle wedge, was fossilized and became part of the lithospheric mantle, and later melting stages melted initially the lower parts of the mantle where thorium, uranium, rubidium, and REE enriched the mantle, but niobium was depleted. And these are the north-south dikes, and later melting occurred from deeper parts of the mantle where niobium enriched the mantle. So this was my master, and it was fun going back to it, and thank you very much.
אוקיי. אני חייב לציין כשרונית הביאה את כל התוצאות, יכולתם גם לראות את זה בשקפים, אם היא לא הייתה צובעת את זה בצבעים שונים, זה היה ענן אחד גדול. ואז רונית הביאה את הרעיון לחלק את זה לפי הכיוונים של הדייקים, שזה נחמד לקחת גיאוכימיה ולקחת גיאולוגיה ולעשות מהם משהו ביחד, וכשחילקנו, פתאום ראינו את המעבר הזה, רונית ראתה את המעבר הזה בין 300 מיליון שנה של וולקניזם קל-קלקליני ל-500 מיליון שנה של וולקניזם אלקליני. עד היום הכל קורה דרך 3 דורות של דייקים שהם בערך מאותו זמן, סיפור די מדהים. אז תודה רבה רונית. תודה. מה הבעיה? כן. בוא, אתה תשים את זה עליך ואני אספר עליך משהו.
עושה את זה באנגלית.
I can do it in English, okay? Okay. I feel a bit strange because this part is kind of my part also. Ronit was the first student of Moti and Ishai was the first student of me, and we did the master together. But then he realized that there is someone who understands much better about the mantle and about basalts, and he went during his PhD, he went to Moti for a lot of advice, and we published together out of Ishai's PhD on the basalts of northern Israel and the Golan. And then later Ishai decided to make a switch, somewhat like Motti. Maybe he learned this from Motti too and went into oceanography. But still, even though he's now a fully established oceanographer, he still keeps an eye for volcanic rocks and for basalts, and from time to time there's one more paper coming from him about this subject. And he's doing all this from his position at Bar-Ilan University as a professor in Bar-Ilan University. So Ishai, please.
Thank you. So first, a few words about the birthday boy. I first met Motti in my first year in the university. He was a teaching assistant, I think, in the course of Earth Materials. And I even remember a comment I wrote something about toleitic basalt, and the comment was, "Are you sure you know what a toleite is?" That's what I remember from back then. And then I was separating pyroxenes for Motti in my second year, pretty boring work. And then Motti went for his postdoc, I went back to the Golan. We met when Motti came back from Caltech on the staircase here, I remember, and Motti was yelling at me. Why? Because I dared writing in my master thesis that the mantle there is enriched. And he told me that maybe I don't know, but all these illusions of Bailey are not relevant anymore. Mantle metasomatism doesn't exist. He changed his mind later on. In any case, both Motti and me share a love. It's a love to the Golan, it's rocks, it's people. Motti joined in his army service the first kibbutz of the Golan, Merom Golan, in the city of Quneitra, the capital. Then it moved, here's the gas station, Motti, and then it moved behind the cinder cone of Tel Bental. Then, several years later, I joined the kibbutz that was also established in the city of Quneitra. And so we started, and then it moved to the center of the Golan. Never mind, but we both loved the Golan on top a lot before we became geologists. This is a typical Motti, lecturing in Kedem to the Radium Radon people in a meeting we held here in 2010. 2 hours of talks to people about in Kedem, left them exhausted, so they had to relax. In any case, back to our subject, Dead Sea Transform. Actually, I'm going to talk not about the mantle, I'm going to talk about the relations between the Dead Sea and volcanism. Those who are not familiar with, this is the Dead Sea Transform, of course, 105 kilometers of left lateral strike slip fault. This is more in the area I'm going to talk about. Where is the cursor? This is the Sea of Galilee, Hula Valley, Golan, Galilee. I will also mention something about the Carmel-Gilboa fault, and also notice that here north, between the Sea of Galilee and the Hula Valley, the fault is split into two, eastern segment and the western segment, and I will talk about it or mention it later. These are the basalts. These are what we call the Arabian Kharats, the Western Arabian Kharats. Kharats are desert, volcanic field, and we will be mainly talking about this. This is the Kharat Asham or Kharat Ashama, one of the largest of the volcanic fields, and here the Dead Sea Transform is crossing in at its northwestern end. The volcanic fields here cover about 200,000 square kilometer. This one by itself is more than 40,000 square kilometer. And dates are from the Oligocene, 31 million years. Association with the Red Sea, no doubt about it, even though asymmetry, almost no volcanics on this side. But Dead Sea Transform activity started no earlier than 21 million years, so clearly it's not that the magmas here are due to the Dead Sea Transform, also from their distribution. Lot of works about why there is magmatism, and I'm not going to talk about it at all. I just show this picture to those who are interested from Kemp and Rubel. Some people say it's active volcanism, like Tzvi, White and Mackenzie, others. Some, like Motti, at least in the past, thought it's more passive volcanism, extension related. These people say it's partly the early is extension related, the later is active by a stenospheric lobe going from the Afar plume northward, crossing the Red Sea and into the Arabian Peninsula, etc. Other question like lithospheric versus actinospheric. Okay, we are not going to talk about it. We are going to talk about any kind of relationship between the Asham, the Ashama field, volcanism, and the Dead Sea transform. And as I said before, it's not about petrogenesis, how magmas form, it's more about plumbology. Like, does the Dead Sea transform has an effect on the channeling of magmas to the surface? Another secondary question, actually this was, we were mainly occupied with it when we were in the field school in the Golan. Is there any real temporal pattern of volcanism in this field? Like, I mean, when you look at the Israeli side of the story, of course, I mean, here it goes from the Miocene to early Pleistocene in the eastern Galilee. Here it goes from Pliocene to middle to late Pleistocene, or you can go from southwest to northeast. Is it true, or is it just because we look at a very small scale? So let's start with the middle Miocene. This is an updated map from a paper with Ariel. What I did here, that's not from the paper. What I did here, I took the eastern side 70 kilometers backwards, like a restoration. Why 70 kilometers? I took middle Miocene 14 million years or 12 million years ago. I said maybe it went 70 kilometers during this time. And what we can see is that the middle Miocene volcanism here, or the whole structure of the Asham, these are the pale colors, they are all the line more or less northwest, southeast, along this structure of the Azraq-Sirhan Graben, which is a very old structure, a lot before magmatism, and the Carmel-Gilboa Fault, which is probably early Miocene, maybe earlier structures. So the Miocene volcanism clearly has nothing to do with the structure of the Dead Sea transform, so we skip it. But if we look at more recent forms, we see what Tzvi was telling us 30 years ago. We see these lines. Yeah, so now Rani Calvo took, now we have GIS. So Rani Calvo took and made a random cone-to-cone GIS analysis just in the last month. And this is a general analysis of all the cones here, hundreds and hundreds of cones, from the Israeli Golan to the Syrian desert. These are specific for the different areas. And you see that it's a very random cone-to-cone alignments. Altogether, alignments are 330, 340 degrees. And assuming that these alignments represents kind of lithospheric dike systems, and assuming pure shear, then we are talking actually about north-northwest, south-southeast contraction, and this is very nicely going with a north-south strike-slip activity. So bottom line, even without talking about specific times, we are talking here about something related. At least the cones know the Dead Sea transform. They know it. Yeah. The question is what is known, but okay. So let's start from the Pliocene, 3-5 million years. It's all this purple. There is magmas on both shoulders of the transform, let's say it like this. But, moreover, there is a big chunk of magmas, lavas, intrusions here in the deep boreholes that were drilled in this pull-apart basin, the Kinnerot Valley. Moreover, when I do again a little restoration for the last, let's say, 4 million years of 20 kilometers, and I do it on the eastern fault, why? Because we have different evidence that at least during the last several million years, there was hardly any offset on this side. So I do a restoration here. So what we get is the Pliocene basalts, that's on the eastern shoulder, that's their northern limit. Here, that's the northern limit. While along the transform, we see kind of a lobe, extension northward. So without getting into it, what is this extension mean? Bottom line, the Dead Sea transform is friendly to magmas. It's a conveyor. It lets the magmas go east, it lets the magma goes west, it lets the magmas accumulate within, and already Tzvi said that it's not accumulation of lavas from the outside, it's lavas erupting within the pull-apart basin or along the transform. So that's the Pliocene. Going to the late Pliocene, early Pleistocene, 3 to 2 million years. What we see is shrinkage of volcanism on this side. There is volcanism here also below this later phase. There is volcanism here, not so much, but there is also volcanism into Lebanon, which I don't have on this map. Very little islands of volcanism on these sides, Dalton, Alma, those who are from the field, Kerem Ben Zimra, Marut, etc., Ayelet HaShachar. So, but moreover, we showed by geochemistry, since it's a geochemistry workshop, we showed by chemistry that actually these magmas, which I put in a slightly different color, peach, are different than these and these, the pink ones. You can see it here, even without seeing what the axes mean. Very different chemistry. Yeah, also isotope, but I just chose two of the diagrams from a paper in 2012. Very different magmas. These are different from these. And what we concluded back then, based on other evidence too, is that, okay, first, the center of activity clearly shifts eastwards, but second, that the western segment of the fault here acts as a barrier between ascending magmas. Magmas ascending on this side of this segment are very, very different than these. We showed it also for later magmas, but mainly the transform starts being less friendly to the magmas, let's say. It blocks magmas, it doesn't let, not too much magmas along the transform, mainly it goes eastwards. Okay. Middle Pleistocene, and I'm talking here about 1 million to 0.6 million years. It doesn't mean that the Middle Pleistocene stopped then, but then we still have some magmas here. This is kind of between a legend and truth. It doesn't exist anymore, so it's mainly here. The Chatzbani basalts, to those who are familiar with. No magmatism at all here, and a lot of magmatism here. And now when we move to the middle to late Pleistocene, 200,000 to 100,000 years, no magmatism here. This is 800,000 years at all. And magmatism only on this side on the eastern shoulder. Moreover, there is no volcanism between 600,000 years and 200,000 years. Post 100,000 years, no magmas next to the transform. It goes all to what we call the Little Edja and toward the Syrian desert. So the magmas are running away from the transform in the last 100,000 years, and you can see it here without words. 2 million years Galilee, Golan, further into Syria, and Safa. Everybody can get in Google Earth and see Safa. Super impressive volcano. And again, Syria, everything happens, but the Smithsonian says that there is reports from newspapers in 1850 that there was a lava lake in Safa. So whether there was a lava lake in 1850 or it was 800, a millennium before, never mind, very, very, very fresh lavas. So volcanism migrated, and you can see the scale. This is 120, 130 kilometers from the transform. So, and there was the break. I'm showing it also here. These are argon. Now we have even more. A lot of argon ages from the Golan. And you can see of the northern and eastern Golan, and you can see very clear. Early phase, 1 million to 600,000 years. Late phase, 200 to 100, actually mainly 100 to 130,000 years. That's the period. Yeah. So why? Why activity migrates? Why volcanic break during 600 to 200,000 years? And we have now more and more evidence about the development of transpersive regime in the northern Dead Sea transform. For instance, of course, Rami's work. This is from a 2014 by him, a paper by him. Clearly falls subsurface, the Shechumit hill in the center of Kiryat Shmona that we all know. Clearly there is transpression in this area. And here we come to Perach. Perach, Nuriel, started working on calcites in the quarry of the Kfar Giladi along the Kiryat Shmona fault, north of Kiryat Shmona. And she was working on two different calcite precipitates, some of them on the strike-slip faults, striking north-south, others on veins which strike east-west. Now, veins striking, these ones. Veins striking east-west means north-south opening, means, assuming pure shear, east-west contraction. So she was working on the two of them, and she was mainly looking for syntectonic calcites and post-tectonic. Syntectonic means like here. This is syntectonic, you see the twins, etc. This is post-tectonic, feeling on top of the fault. Syntectonic means strike-slip work. Post-tectonic means strike-slip faults stop or weakens, and there is contraction east-west, normal to the Dead Sea transform. And during the course of a paper that we published in 2020, she took a specific vein that showed a multiple history. It started opening, filled, calcite was going into the vein. The vein stopped opening, so the calcite filled the vein, and that's what she called an hiatus. And then the vein reopened again, and calcite started working, filling again. You can see here the section, and she dated these. She dated these, and and she had a hiatus here, and she got 350 to 240,000 on the first phase, and the last phase was 50 to 30,000 years, and hiatus in between. So I'm coming to the end. This is the vein I was talking about. Ages in times where the vein was opening. Vein opening means contraction. These are all the veins she was working on them before, but not multiple, with multiple history. So you see, this is the hiatus in the vein I was talking about. This is a shorter hiatus. Still, 100 to 140. These are periods of strike-slip faulting. So you see, strike-slip faulting concentrates here when there is, these are the argon-argon ages. Strike-slip faulting concentrates here, although it goes a bit also here. But clearly, there is a hiatus on this period of the 200-something to 100,000 years, hiatus in vein growing in this specific vein, or around the time where main activity was. So there is a relation between vein growing, strike-slip activity, and basalts. And the idea is, when there is vein opening, there is east-west contraction, no volcanic activity. Remember, 600, 200,000. No, we don't have all the way, we don't have calcites all the way back down to 600, but that's the concept. Activity on strike-slip fault, no vein opening, then there is resumption of volcanic activity, and that's the idea about this break. So this is the concept. The concept, the same like I said now, where during 1 million years to 600,000 years, there was relatively small, I don't say there was no contraction because there are other evidence, but it was relatively little. So there is volcanic activity also along the transform and here, and then the same about during the late phase, although there is no along the transform, but there is close to the transform, 15, 20 kilometers from. On the other hand, during 600 to 200,000 or during the last 100,000 years, no activity. Why? Because contraction resumes, veins, etc. No way for the magmas to come out. At least it's not convenient. So summary, Miocene, volcanism did not hear yet about Dead Sea transform. Pliocene, Dead Sea transform friendly to volcanism. Early Pleistocene, 3 to 2 million years, volcanism starts shifting eastwards, maybe contraction starts, I don't know. And western segment acts as a lithospheric barrier. 0.8 million years, last volcanic activity along the transform, everything shifting east. Last 1 million years, volcanism on and off, related to strength of east-west contraction. And the last 100,000 years, volcanism, no more in the Golan, continues further away, as Safa, etc. Thank you.
תודה רבה לשי. שאלה? לא. אוקיי. 100%, אז תודה לכל... כן.
אנחנו רוצים לעשות שינוי יש עוד משהו אחד עכשיו.
אוקיי.
אבל...
אוקיי, בסדר. אבל בכל זאת, תודה לכל הדוברים של הסשן הראשון. Thanks to all the speakers of the first session. And
So, since we're a bit ahead of schedule, I want to use this time and invite Ariel Hyman to say a few personal words. And... כן.
מוטי, מחייך. קצת לא גיאולוגיה, אבל קצת כן. 6 זיכרונות עם מוטי. זיכרון ראשון, לימודים בשנות ה-70. הייתה או לא הייתה תנועה אופקית של 100 קילומטרים לאורך הבקע. רפי פרוינד ונחמן שולמן מתווכחים, ואנחנו סטודנטים צעירים ונאיבים לא מבינים, ובוודאי לא יודעים למי להאמין. אל הלימודים הגענו כולנו פצועים וחבולים בגוף ובנפש, ממלחמה שלקחה כמה מטובי חברינו. באני לשמוע תורה מפי בנטור ורייס, ומהצעירים שיושבים כאן, רפי, סטארי, ישו, גרפון, איתן ועמיתי. מוטי, שגדל על גבעות הכורכר של רמת גן, ולמד בכיתה עם יוני רכטר, היה גדול שכזה, 2 לפנינו בלימודים. המכון לא היה והמחלקה לגיאולוגיה הייתה קטנה, ואפילו טקטוניקת הלוחות התגבשה רק אז. היינו מגובשים, ומוטי משכונת המקשר היה פיבוט ומגנט חברתי, מככב בין השאר בערבי הרצאות על טיוליו בעולם, שבהמשך הפכנו אותם גדי ערן, מוטי ואני, לערבי גיאוטק מקצועיים ומעליבים. גדי ערן, חברנו האהוב, שעלה על מוקש בסופה של מלחמת לבנון הראשונה, ושיד חדרו בהדסה בילינו, מוטי, אני ואחרים, 10 ימים מורטי עצבים עד שנפטר. צעקנו וחטפנו אבנים וכללות בהפגנות של שלום עכשיו שרק נולדה, ונשכנו שפתיים ממותו של אמי גרינצוויג, והקשבנו בגשם הכבד ובקור למילותיו המנחמות של עמוס עוז. שנים של אהבות צעירות, חתונות ראשונות של חברים, וטיולים להודו ויפן, לדרום אמריקה, ובעיקר שוב ושוב לגולת אל עזרק, ג'בל סירבל וואדי הפילים שבהר הגבוה. עברו השנים, חלק הלכו מאיתנו, רובנו הלכנו מירושלים, ורק אתה מוטי נשארת בעיר לשמור על הגחלת. וכל אותם רגעי אושר ותום של פסגות ההר הגבוה וחופי סיני הזהובים, התמימות והאהבה נותרו מתוקים ועמומים, ואולי הם, לפחות בחלקם, עיצבו את חיינו וגורלנו המשותף לימים יבואו. זיכרון 2, קרני חיטים. שנות ה-90 המוקדמות, עודד, מוטי ואני מטפסים במכונית המקרטעת בדרך העולה להר שיפון, תחנתנו האחרונה במסגרת תחנת קורס הוולקניזם שעודד ואני מלמדים מאז ועד היום. השמש בפאתי מערב, הירח מבצבץ לו מעל האופק הסורי ממזרח, הגולן הרומנטי על שפע קילוחי בזלות דלווי והכיסוי מונח תחתינו, והסרטוטים המופלאים של דורון מור בידינו. לפתע מוטי מודיע בעצבנות משהו שהתרמיל שלי לא כאן. כן, מוטי המפוזר, השארת את התרמיל בקרני חיטים. וכך בדרכנו הביתה אנחנו מטפסים רגלית פעם נוספת אל קרני חיטים על 4.23 מיליון השנים שלה. מסביב דומיה ושמיים זרועי כוכבים, ורק הירח מונח לו שם מעבר לכנרת ממזרח מעל לגוש האפל של רמת הגולן. מרחוק מבליחים אורות פוריה וכפר חיטים, ובמהלך הצעידה השקטה הזו מתבהרת החברות והידידות הנרקמת לה לאורך השנים, שיש בה אהבה משותפת לגיאולוגיה, אבל הרבה מעבר לכך. ובתוך החשיכה והשקט וכל הקסם הזה, כמו שמוטי מספר, מזמזם פתאום הקול הטורדני של הטלפון הסלולרי. מישהו מהילדים מבקש שנקפיץ אותו לחוג הקראטה. זיכרון שלישי מרום גולן, אוגוסט 2014, שבת, 6 בבוקר, גבע הנכד שלי התעורר וכדאי לצאת החוצה כדי לא להפריע לישנים. קרני השמש הראשונות מסנוורות, אבל מבעד להן הדבר היחידי שאני רואה זה את שטיין על הדשא עם כוס קפה. שבילי מרום גולן מוכרים למוטי מאז שהגיע לקיבוץ כנחלאי ב-1969, כשמרום גולן עוד הייתה בקונטרה. יום קודם, בבית הקברות הקטן של הקיבוץ בלאו של הר בנטל, 0.1 מיליון שנה, אני מקשיב לדברים של מוטי המדבר על השורדים, ומבין פעם נוספת את הפער העצום בין הבזלות והקסנוליטים שדגמנו ואספנו בחרמונית, כדי שאני אתארך והוא יתאה על מקורם, לבין החיים האמיתיים. ואני מצטט רק קטע אחד מתוך הדברים שמוטי נשא בפנינו וקרא לקטע ולנו השורדים. כשורדים הגענו לכאן היום, שורדים של מערבי הדגן בבקעת הירדן וארץ המרדפים, של התקפות רימונים במחנה שתי, של ציורי לילה במרג' עיון, של הצלפים במוצב אתונה ג' של החווה הסינית והחיץ החקלאי, ושל פגזי התותחים במובלעת הסורית וכאן בין שבילי הקיבוץ. ואז ממשיך מוטי, פתאום הפכנו לאמהות ואבות, ובנינו גדלו וחזרו למרג' עיון ולג'נין ולמנהרות שמתחת לסג'איה ורפיח. אורי, בנו של מוטי, וכל 4 בניי היו באותו היום בעזה וסביבתה במבצע צוק איתן. זיכרון 4, שיחות טלפון, תמונה ראשונה. באחד מהכנסים של ה-AGU בסן פרנסיסקו חלק מוטי חדר מאיתמר הבן של עודד במלון, שבו השתכנו מוטי וכל המשפחה של עודד שהגיע מהשבתון באנגליה. בבוקר טיילנו משפחת נבון, מוטי ואני, אל גשר הזהב בטיול קצר שלא יישכח. בדרכנו לכנס חלף על פנינו ניק שקלטון, הגיאולוג המוכר. מוטי אומר לנו, תראו איזה מזל יש לנו. הבן אדם שקלטון, אבא שלו הוא מבחירי הגיאולוגים באנגליה, ודוד שלו הוא סר שקלטון מאנטארקטיקה, גיבור אנגלי מיתולוגי. תראו כמה מחויבות הוא סוחב על הכתפיים שלו, אבל אנחנו מה אכפת לנו? אנחנו בנים של סוכני ביטוח ומהנדס, לא חייבים שום דבר לאף אחד, עושים מה שבראש שלנו. מאז, כל מי מאיתנו שמגיע לסן פרנסיסקו מתקשר לשני להעלות את זיכרון הפגישה. תמונה שנייה, מוטי באחת מציאותיו ללמונט ואני גם בסביבה, פגישה בבית קפה על גדוד ההדסון, עוד מפגש טוב בינינו, ונכון, מאז כל מי שעומד על גדוד ההדסון מתקשר. תמונה שלישית, ערב, מוטי על אוניית הקידוח במרכז ים המלח, וכמו שאתם מנחשים, טלפון ממנו בכל ערב שהוא על הסירה לאור ירח. תמונה רביעית, אמסטרדם, בשבוע שעבר. אני שולח למוטי תמונה של מסעדה שנקראת מומו. מיד מקבל תמונה חזרה של חנות בגדים בטוקיו עם אותו השם, ועם הכרזה של מוטי הוכחה שיש אלוהים. אז מוטי, שנשוחח גם מטוקיו ואמסטרדם, ואולי גם נוסיף את אלוהים לשיחותינו. זיכרון חמישי, קורונה. יגאל הראל וגם מוטי ואני עסוקים בימים הראשונים בחישובי זום מתי היו בישראל 10,000 חולים, והמדינה, כך הבטיחו לנו, הקברניטים תתמוטט. מוטי שולח קרב גידול אופטימי של פרנסיס אלברטה, החבר שלו, ואנחנו נתלים בו למרות שאנחנו לא מאמינים לא לאלברטה, לא לגרף ובטח לא למוטי. מרץ, עם ישראל בבתים, אף אחד לא יוצא, אבל מוטי שולח לי סרטון מההפגנה הראשונה, הפגנת המכוניות סביב הכנסת. כמה שבועות לאחר מכן, מוצאי שבת, ואני נוסע במכוניתי, הפעם לא כל כך מקרטעת, לירושלים. לי זו הפעם הראשונה ולא האחרונה בבלפור. עוקף את מחסומי המשטרה, חונה בעמק המצלבה, וצועד במעלה רחוב עזה, וזוכר את ההנחיות של מוטי. תגיע לכיכר, אני שם, יש לי מקום אסטרטגי ומבודד, אתה כבר תמצא אותי. מגיע מוטי אכן במרכז הכיכר, על המדרגה הגבוהה מעל כולם. כל שבת, מהראשונה לאחרונה. אני נדחק בצפיפות לכיוונו של מוטי, הוא פוגש בדרך, בפעם הזאת או בפעמים אחרות, את רוני אלנבלום, אללה ירחמו, את גידי בר, עודד נבון, אמיר אידלמן, אמיר סנדלר, עזר זילברמן, יהודה אנזל, ועוד מהיושבים כאן. מתייצב ליד מוטי בעמדה, ויחד עם הטופים ועם מוטי עומדים ושואגים את המנטרות הידועות. ועם ההתלהבות של מוטי, היה נדמה לי שאם לא אחרים, הוא לבדו, אם צריך, יחליף את השלטון. הצלחת, מוטי. זיכרון שישי ואחרון. הנסן. בשנים האחרונות אימצנו לנו את בית הנסן, לשעבר בית החולים למצורעים. באמצעו של יום, לפני שיעור באוניברסיטה או אחריו, התיישבנו שם לא אחת לתכנן כתיבת מאמר משותף על צמח. לא יצא מזה כלום בינתיים, אבל נדמה לי שאף אחד מאיתנו לא הגיע לשם באמת בשביל לשבת לכתוב מאמרים. הגענו לשוחח מעומק הלב על חוויות משותפות שיש לנו ב-45 שנות היכרותנו, לצעוק ולכאוב ולטפל מעט בעצמנו ושרידי ההלם של מלחמת יום הכיפורים. באנו בשביל לשתף על אתגרי החיים, על מה הלאה, לאן פנינו, מה חשוב לנו, המשפחה, מה מהנה אותנו לטייל בארץ ובעולם, ובעיקר עם הילדים והנכדים, למשל איסלנד, מה מאתגר אותנו לחקור וללמד את הדור הבא, הסטודנטים והקהל הרחב, ומה בסוף עוד חשוב לנו, הפאקינג מדינה הזאת. וכל שאחל לך מוטי מלבד עוד מאמרים, סטודנטים, נכדים, בריאות ואהבה, זה שנמשיך להיפגש בהנסן שם קוד עוד שנים רבות. וזה שאני אוהב אותך מוטי, נדמה לי שמיותר לומר.
תודה רבה. קופי טיים.
דיסקנטי שכנראה לא עובד.
זה שם מחשב אין בעיה. איך אתה מתחבר? עם כזה או כזה?
כזה, יותר כזה. אתה לא השמנת יותר מדי במערכות. אני לא יודע.
איך אתה בדרך כלל מתחבר? או שאתה רוצה ש... אני מבקש דיסקונטים ממישהו, זה גם אפשר. הנה דיסקונטים. תראה מה זה. שכה?
זה שלי, הוא איכשהו לא עבד. אני אעשה את זה.
אחד מאסטר.
שלום, מה נשמע? בסדר. אני באה במחשב ומתחברת?
איך שבא לך, אבל אם יש לך את זה על דיסק הכי קל, את ב-PC?
כן, אין לי את זה על דיסק. אני יכולה להבין. יש לך דיסק.
אני אנסה, אבל איך שזה לא עובד. אני השתמשתי בזה שנים.
קחי אחד מאלה, מחזירים מצגת.
יוסי בטח לא היה.
לא, זה לאו דווקא סטודנטים שלו. גם אישי לא היה סטודנט שלו.
אני לא הייתי סטודנט.
אתה היית סטודנט שלו.
מה? מה?
בדיוק, אתה עדיין.
אתה נוסע עם דיסקנקיה או שאת...
משהו יודעים לי.
יש עם הדיסקנקיה שלי לא עובד.
אין לי דיסקופים.
אין לך? או יש לך?
יש לי מחשב.
איזה? טוב, עם כזה?
כן, כן.
אז את נכנסת פה.
מעולה, אני יכולה לראות אותם במחשב?
כן, אם את רוצה.
תן לי רגע לנסות...
איזה מהם? זהו זה.
אני משאיר את זה.
רגע, סליחה, יש פה את זה, זה מה שאתה רוצה.
בדיוק. זה מה שהוא רואה פה בצד. בצד הזה.
פה אני אשים בינתיים שיתאים את עצמו.
אני להביא לך משהו להשתתף.
לא, אני תכף אצא, אני...
נפל פה משהו. רגע, אלינה?
ככה, שיכולה.
אלינה? נפל לך מהמדונה משהו. קחי. זה. רק נראה שזה תופס?
כן, הנה, אני שם לך עכשיו. פה. לא רואה אותך.
היא בכיס האחורי שלך, בועז. זה כמו משקפיים, בועז.
הנה, אתה מסוגל את זה.
זה פשוט...
אז תשמע, אז כשאתה עולה, זה לא יהיה מחובר. אני אחבר לך את זה. אתה תסגור את המשהו.
אוקיי, אז כרגע אני יוצא. לא לשכוח.
כן, כן, בסדר. אז אני יוצא מזה. אנחנו את זה לבועז.
את מתי יוצא?
כן.
מה שרואים את המסך?
בסדר. שומעים פה אנשים. אתה מסודר, כן? אז אתה יודע שתסתכל. זה לחץ על זה. רגע שנייה. מעביר את זה לזה. תקשיב. כן, עכשיו תסתכל רגע. סטיב, יש לו גם סרטון.
לא בקהל, אתה פה בעולם, אני צריך לדבר, כן.
רואה את ההוא?
קר מדי. אנשים מתלוננים שקר להם.
יעל,
תודה.
זה הסרט, זה לא...
לא, אז יש לו סרטון קצר של דקה כזה שהוא אומר רחוק וזה, ואז יש לו פאורפוינט.
גם סרטון.
זה כן,
זה כן. לא נמצא פה בשטח.
לא. זה הפליי של סטיב, הוא עושה פליי ושאני עושה את זה, נשאר כאן לעשות את זה. אז אתה תציג, לא יודע, צריך להציג את זה. ואני צעק עליהם.
נא להיכנס. וכבר אנחנו מאחרים בדקה. אוקיי. תשאלי את יעל. תשאלי את יעל. בואי לפה. אורית. בואי לכאן, יהיה לך חם. פה לא קר. כן. שבי פה. טוב, אנחנו צריכים להתחיל. אוקיי. אנחנו נתחיל את הסשן הזה, שזה הצד המימי, הגמי. אנחנו נתחיל בזה. לא שומעים? צריך לצעוק, אני רואה בפנים. אנחנו נתחיל בקטע האמצעי, שזה הצד האגמי, ימי, מי תהום, כל מה שאתם רוצים, שזה הצד שמוטי מתעסק בו עכשיו, בעיקר, ככה זה נראה לפחות, ונתחיל גם כמה מילים ובהרצאה של סטיב גולדשטיין מלמונט, שבעצם כל הקטע הזה התחיל עוד לעבוד בזמן שמוטי היה במקס פלנק אינסטיטוט, בפוסט-דוק. מה? It's in English, okay. Now it's okay. Can you hear me? זה לא בגלל האנגלית, אז אולי פה. Now it's okay? בסדר? Okay. Now it's okay. Okay, so I try to speak not into the microphone. Okay, so we start with Steve Goldstein from Lamont, who was together with Motti in Max Planck's Institute during quite many years back, 1985, not 2085, but 1985, and then was the time that Motti did quite a bit of work on the teams working day and night, and also later. And Steve is actually working on things here in Israel, like on the Dead Sea, and they did a lot of work on the deep core in the Dead Sea, as well as working on cores from the Red Sea. So all this work, they go back decades, and Steve is a very old friend, and he wants to say a few words, and let's hear him.
First of all, I want to say greetings to everyone in Jerusalem. It's been a while. Probably the longest interval I've been away since 1990. And happy birthday, Moti. I also want to say apologies that I'm virtual. In normal non-COVID times, I'd be there. And when it was announced that travel to Israel would open up on November 1st, there was just no way to modify my schedule to allow the trip. So, what I've decided to do is give a live presentation virtually. Even though it's really, really early in the morning here. And Moti, I wouldn't do this for just anybody. But it turns out that over the last day, my early morning has been completely scheduled. And these are meetings that I have to attend, and so I decided that I should be asleep at this time when you're seeing this. So we're going all virtual. My presentation will be recorded on PowerPoint, not on Zoom, for convenience reasons, and so I'll leave now, and hopefully we can successfully switch to PowerPoint. But once again, happy birthday, Moti.
Okay, now we will hear the lecture, and it starts right here.
As this is a symposium to celebrate Moti Stein's 70th birthday, looking at the schedule, there will be a lot of great science discussed here. So what I've decided to do is use my short time on the platform to honor him. So the title of my talk is A Tribute to Moti Stein, Geoscientist, Scholar, Medic. Moti Stein and I go back a long way as close colleagues and as close friends, and we've done a lot of great science together, at least I think, and we've enjoyed a lot of free time together, and our families know each other. But today I'm going to be talking about Moti Stein, the scientist and the teacher. But before I do that, I want to give some context. I arrived at the Max Planck Institute in Mainz in November 1985, exactly 36 years ago. This photo emphasizes just how long ago that was. Moti was there as a graduate student at the Hebrew University and had a Minerva. Now, I've run into people all over the world who know Moti, and people actually tell stories about their first meeting with Moti Stein. This was mine. I was brought to my office, and I found Moti occupied. He said he was leaving for Mainz in a couple of months, as he had to get back to Jerusalem, and asked if he could stay in the office. I said okay, but his return to Jerusalem kept getting delayed, dragging on for 8 months. So in fact, I got to know him pretty well, and he was the guest who stayed. And that's how we started working together. So I'd like to ask the audience, when you think about Moti Stein, what words come to mind? Tranquilo? Definitely not tranquilo. Okay, when I think passionate, intense, enthusiastic, animated, okay, I think of that. Argumentative, definitely argumentative, but also scholar, scientist, teacher, mentor, honest, moral, and I think we all of us who dealt with him knows that he's a good dad, given that whenever we're trying to reach him, he's driving somewhere with his kids. My daughter was out in the field with us a few years ago, and she took a sequence of photos showing Moti being passionate, intense, enthusiastic, animated, and argumentative. Here we go. Okay, we know that was not unusual. I took another sequence of photos a few years later. Another set of words that come to mind on my original list: scholar, scientist, teacher, mentor, and yes, going along with that, once again, argumentative. But that has its own story. Not only is he a scholar and a teacher, he said something to me way back when that showed who he is emulating. And while this is not an exact quote, it gives the gist. He said, "We scientists are like the rabbis who spend their time studying, seeking, and arguing about the truth." And looking at this painting, I'm trying to figure out which one of these guys he represents. Now, one might ask, how does Moti Stein view himself? Well, I have a suspicion, and it's on the next slide. And note that it's two drawings, and note that he put these two drawings together. There you go. And again, he put those two drawings together. And I note that both are wearing clothing representing New York City. But let's talk about his science. I asked the question, what subject within the geosciences does Moti Stein study? And I searched the internet for an illustration that represents the range of his interests and his accomplishments. And it wasn't easy to find something, but the following slide shows what I was able to come up with. As I said, it was hard, but this is what I came up with. You know, some people study magnetism, or faults, or sedimentology, or metamorphism, etc. And I don't have time to go through all of this, but believe me, there's a lot of it in here that relates to Moti's interests and his accomplishments. Moti's disciplinary breadth is reflected all the way back in his graduate studies and his postdoc at Caltech. It probably had something to do with the fact that he had an amazing set of mentors. Chladni, Starinsky, Garfunkel, Wasserberg, and that his studies had amazing breadth, ranging from sedimentary geochemistry to mantle geochemistry to fossil reefs. So let's now talk about Modi's accomplishments. Here's his Google page, his Google Scholar page. Note that he uses the John Lennon drawing. Okay? He has more than 11,000 citations. He has 60 papers with 60 or more citations. That's the H index. His citations are approaching about 1,000 a year, and it's a continuing upward trajectory. That's a record that documents a highly successful scientist. Okay, here I've added the publication rate. We see that it increases through time, and over the last several years, it's consistently high. In fact, since 1913, he's published on average more than 8 papers per year. If we look at how those citations are distributed, it turns out that 2 of Modi's 5 highest cited papers, in fact, are about solid Earth geochemistry. And in fact, another solid Earth geochemistry paper is in the top 10. But in fact, 6 of Modi's top 10 most cited papers are about the Dead Sea. Modi realized early on the importance of the Dead Sea and its precursor lakes as a record of the climate of the eastern Mediterranean region and the seismicity record. And I expect that his success in gaining global recognition of this will be his greatest legacy. This is the gang of 4 that Modi got together to start the modern phase of work on the past deposits of the Dead Sea. It was back in 1990, amazingly, almost exactly 30 years ago. And besides him and myself, there was Hagai Ron and a graduate student named Shmulik Marko. The first time I saw the Lusan Formation, I have to admit I was blown away. As one can see time passing and recorded at high temporal resolution. And our initial objectives were not modest. They were radiocarbon timescale calibration, delineating the evolution and chronology of the Lechamp magnetic excursion, delineating the seismic history and the climate history. As the Dead Sea expands during ice ages and contracts during warm ages, we realized from the beginning that the marginal sediments where we were working are discontinuous, with large amounts of time missing, particularly during interglacials. And that we needed a drill core beneath the lake level. Well, we all know that this ended up being realized through the ICDP Dead Sea Deep Drilling Project, where our goals were not modest. They were to recover the longest, most continuous, and best preserved paleo-environmental and paleo-seismic archive in the Middle East. And our hope was to recover up to 500 to 1,000 meters of core, and we were expecting to span between 500,000 and about 1.3 million years. Funding attempts lasted for about 10 years. It was a lot of work by Moti Stein, Steve Ben Abraham, and myself. We actually managed to get a planning workshop, which was a good start, back in 2002. It took place in Germany for political reasons. And that was a good start, but the project was delayed for several years due to the regional political situation. But eventually it was funded in 2009, and the funding proposal also included a group of people from, basically we ended up with APIs from 5 countries, and drilling began in 2010 and finished in 2011. Drilling the Dead Sea was not easy. In the middle of the campaign, the drill rig needed major repairs due to salt corrosion, and there were some major winter storms that really messed us up. But in the end, what we got was a major success. We successfully drilled 2 sites. From the deepest site, we recovered about 460 meters of core. Turned out to be 220,000 years worth, going back to marine isotope stage 7. We recovered the longest and most continuous, well-dated now climate archive in the Levant Eastern Mediterranean, which serves as an important complement to the excellent speleothem records pioneered by Mira Bar-Matthews and Abner Ayalon. And there have been a wide range of studies, ranging from the biology of extreme environments, to the geochemistry, to the geochronology, to the paleoseismology, to the pollen studies. There are more than 100 peer-reviewed papers on the core now, and a special volume of QSR. For all that, we need to credit Moti's vision. And we should also note that it's really only a portion of Moti's research. Now, his other great success is as an inspirational mentor to more than 40 students and postdocs. And they constitute an all-star list of early to mid-career Israeli scientists. And this is really something to be proud of. All of this was summarized in Moti's citation when he was recognized as a geochemical fellow.
For being an idea generator on overdrive with great enthusiasm for geology and great scientific intuition, for being an inspiration to early career scientists, and for making important scientific contributions to many fields, ranging from Middle East paleoclimate to mantle geochemistry. We would also like to recognize a 2018 fellow who did not attend last year, Susan Trombor.
So, as a final thought, Don't be concerned about turning 70. As they say, 70 is the new 50. And maybe you can help to turn it into the new 40. I want to leave you with a nugget of wisdom from Dolly Parton, who it turns out is just a few years older than you are. And she says, now, people are always asking me, what do you want people to say about you 100 years from now? And I always say to them, I want them to say, dang, don't she look good for her age? Again, happy birthday, Modi.
Okay. So I guess there are no questions. So we can... Huh? Okay. Now can you hear me? Okay, fine. So this day, or this session now, is starting with my lecture, which I came here also as a Moti student actually, because Moti introduced me actually to the realm of reefs as rocks, or as not as I was studying them before, in the sea, and how they act and how they thrive and grow, but what you can do with them more. And that we shared also. The first student that worked on, who happened to be just here, is Kika and Mark, which we are very happy that she is here, but it was a long time ago. So let's start. So what we want to start is first with a tribute to the people that are part of this work. And there are two more. So these are Yoni, which is here, Amos, which is here, and the students that worked on that, Neta and Mayan. Mayan is also here. And Yael, which joined a little bit later, but she did quite a bit of work. And the king of the day is here, Moti, the last but not least. There are other two students, which you will see later in the talk. Anyway, this was also funded by several grants, also from the ISF. Now we will look at it, but start with reefs. So, looking at the reefs, and this is the One Tree Island Reef on the Great Barrier Reef. And if we zoom in to here, we see the modern reef over here. But if you look at that part, and now you go here, you see a fossil reef, which is above sea level. This is the reef. This is Bradoptide actually, sitting and standing on this fossil reef here, corals. And this means that the sea was somewhere higher than it is today, and depends what is the age of this reef. So we know where is the sea level at the time. And here is again something from back, Moti's history in Papua New Guinea, where you see, why it is not, okay. You see reef terraces. Reef terraces, the higher, the older is the higher. You see what is the height of this, go up to 400 meters above sea level. But the ages here, as you go up, they are older, because this is uplifting area pretty fast. So if you can date these reefs, as Moty did in part of his, during his postdoc, and you can reconstruct part of the sea level curves over time, with time. There is another good marker for sea level is, let's say, this beach rock like you see here in Heron Island, also Great Barrier Reef, but we won't talk about that this year. So we jump to the Gulf of Aqaba, where we work on reefs around, and especially to this part when you see the nature reserve, the underwater observatory, and the Tur Yam and the Eilat Promenade, which we will devote some time to. Okay, so this is in Aqaba. This is an elevated reef, actually. So this is a reef above sea level now. And here you see Yoni. You see it's here. Now is working on this reef, or standing on it. On the other side, if you would look, you see somebody walking there. And that's a position that Moty is really known for. Here is walking around in the field, looking here, looking there. But the second best position that he likes is this one, as was mentioned already over the phone. Talking of the phone is the second best position. So anyway, if we want to know where was those reefs, we have to date them. And this was done not only by carbon-14, because all the reefs can be done just by uranium-thorium. And maybe we take a crash course, what is a uranium-thorium dating, which was already mentioned in one of the talks. So this is the series of uranium-238, and it goes like that. Which goes down, it is alpha decay, and if it goes to the right, obliquely up, it is beta decay. And this is the whole series. And these are different elements also of this, but such a series should reach what we call secular equilibrium. Secular equilibrium means that decay, after about 1 million years, if you start, you get to a situation where the activities of all of the members in the series is the same as the activity of the grandfather of it, the uranium-238. But it is activity, it is, excuse me, okay. What I mean by secular equilibrium is the activity is the same. Now, the different elements have also different chemical characteristics, like uranium tend to be dissolved in water, while thorium has affinity for solids. Now, if we go here, just to the upper part, the decay looks like that. The uranium decays to thorium-234, and you get a recoil. It shoots an alpha, a helium atom. And then it decays beta without, and again, recoil, alpha, and go on. What's going on here is because of this recoil, the lattice of the crystal is damaged, and weathering takes out preferentially a little bit more uranium-234 than uranium-238, and upon weathering, the ratio in the ocean becomes 1.15, a bit higher than 1. It's just a decay rate, because the concentration rate is still, the concentration, uranium-234 is still about 1 million less or smaller than uranium-238 in concentration, but the decay, they are in the same level, it's higher even. Now, if you are a coral growing in the sea, what you see is something like this, because you see no thorium, you see in the water, you see uranium, and you incorporate uranium and start to grow in this ratio, 1.15, and you start to grow that way. Okay, so time is on the x, and we see here the thorium is growing up, uranium doesn't change because it is so slow, and uranium-234 goes down, and as long as we have here a difference between uranium-234, thorium-230, and the uranium-238, we have a clock. When it ends up here, the clock is finished. Okay, so now we come to the second, or another heroine of this talk is Noah Weil, which did her study here, the MSc. This is the terrace of the Tur Yam. Here she's sitting, standing on it, mapping it. This is how it looks like. Or where you see that there is a reef here. If you look here, this is a beach rock and this is a reef. And if we zoom in, you see it like that, the beach rock and the reef. And she did careful mapping in a very fine scale. You see the scale here, so you see that it is a geological map in a very small scale with 3 sections here. All of them show here reef rock. And when she came dating this, using this method, she gets an average age of about 6,000 years. But if you take and put it on a graph like that, which is, you have time here in kilo years, and you have the elevation of the reef, you get it here. Now, if you put in the sea level curve, or the calculated sea level curve for the air, you see that it fits pretty well. If you add some more data, like here from Yonis, PhD, here from the Elite Promenade, and Tur Yam, also from Yonis, it fits pretty well, but do we have also some evidence for this fast rise? So for that we need the second student, the second heroine here is Osnat, PhD. Here she's her MSc, now PhD, and you see her explaining again to whom she's explaining the work. You see it by the head, you can see that it is also Motti sitting there. So she did her work in Eilat port here. Oops. Oh, what's that? Okay, she did her work here. And looking at many courses that were done in Eilat, she took and did, let's say this is an example of one of the section of the geological section, with the reef unit here. And when she dated those, you see she gave those data, but if you look at the pattern of it, this is in one of the cores. This is in another 2 cores together. There is another one, but you see that they end up, if they intercept the sea level curve, at about 9,000 years. So it means that when sea level, they started to grow and sea level was there. And there is another point, but still, this is by no means, it is a very detailed reconstruction of sea level. And these corals also were buried, they're growing slower than the sea level rise, and they got buried, so they are not with us here today, they're just in the drill holes. Anyway, so we get a conclusion of what the first conclusion, that it looks quite good, but it is not, better resolution is needed, and And Motti, last week, I think, just not a week ago, you submitted a proposal to the ISF to do this exactly, but in higher resolution. Okay, so can we get also information like Palo information for that? For that we have the work that we did with Neta, Mayan, which is here, and Yoni, which is here during his PhD, in those places in Aqaba. The mapping of Neta shows those reefs, the reef terraces, R0, which we know already because this is the same reef that was on the other side in Noah's work. R2 and R3 were mapped here, and just we have to know what are the ages of those one. And you see a section here. This is these different reefs. This is a section of those. And if we just zoom into one of them, this R2, and it looks like that. You see it here, and you see what is important, that you see all three ingredients, all three zones of a reef, reef flat, back reef, and the beach, which means that this is a typical fringing reef, which is a reliable marker of sea level. But when you come to this reef, you take it and you see, wow, it is calcite. What you do? But what turns out that actually, from getting this calcite, it gives you another information. What you say here in Hebrew, in 3 words, actually you have to say in English in 8, which is amazing. Anyway, so it means that the corals, or the reef, was crystallized from aragonite to calcite. So it says something about the hydrologic regime. And can we date those? So how it becomes from, or how it recrystallizes, you see a reef growing here. There is another reef outside, which was an older one. And what happens if sea level goes down and you have to have fresh water around? It means that if you have a coastal aquifer with fresh water, then the fresh water goes through, like here, you see it here. The reef goes through fresh water and it recrystallizes to calcite, and then it is aging again as in calcite. So it starts aragonite, recrystallizes. Then it means that what happens is that when you recrystallize from aragonite to calcite, you lose uranium because the distribution coefficient of uranium in calcite is lower than in aragonite, while thorium, which has an affinity for solids, stays the same. So on that, we constructed the model for open system dating. And this goes like that. You take a coral which has 3 ppm, let's say, of uranium. It aged 25 kiloyears, and then it recrystallizes. It means that it loses uranium. It goes there. What we did here, even lost the whole uranium, but theoretically, like we lose the whole uranium, and then let it age as calcite for another 100,000 years. It looks like that on an isochrone. This part gained thorium, and this part loses thorium versus uranium because it doesn't have enough uranium to support the growth of thorium even. Okay, so you have a slope and you have an intercept. From there, you can guess age of recrystallization. Now, if you look at the 234 to 38, they look like a straight line after the time, because when those that lost the whole amount of calcite, the whole amount of uranium, they should go through zero. So it is a line that goes to zero. It has just slope. Now, if you go to the real world, let's say for this R2 terrace, you get this. So you get a slope, which gives you a slope and an intercept due to the time of recrystallization, and the 234, 238, just the slope, you plug them, you get the time of coral formation. Okay, so if you go back to that map, now we can put dates there, and what you see that R2 is 124, and R3, which is higher, is also older, and the time of recrystallization, it was recrystallized in that time. So it was recrystallized later when sea level changed, and from there we can draw this thing. Let's say, what was 120, 130? You had sea level here, and you had fresh water because you see that there was recrystallization. This was formed. This R3 was already 130 kilo years old, and it recrystallized here at 124, while at that time R2 was forming. And how it goes with the sea level curves, this is the sea level curve. You see that the sea level curves show at that time high stand. Then sea level dropped and this place was dry. Then sea level rose again here. And then R2 recrystallized with this fresh water. And at present what we have, so this was recrystallizing at that time. And now this is the situation, but there is no fresh water. There is no recrystallization. And R0, and this is growing, and R0 is not recrystallizing. It stays aragonite. Here. Okay. It means that it is drier than it was. Okay, so if we sum up, what is really, those are not that important. You saw them now in the pictures, but the fourth one is important. Conclusion that during the high stand, during the last interglacial, conditions were wetter because we had also a coastal aquifer with fresh water that could recrystallize the aragonite to calcite. Okay. Thank you. Okay, we go on. Okay, next one is Revital Bookman from the Haifa University. She did her master's and PhD, actually it was a PhD just, with Motti as one of her advisors on the Dead Sea. And what she will talk here is actually not on that thing, it's showing that she is advancing, which is important. Okay.
אני אגיד כמה מילים בעברית, אני קצת מתרגשת מדי בשביל להגיד אותם באנגלית. אני מאוד מתרגשת מהמעמד הזה פה להיות כאן, יום הולדת שמח. אני אגיד שהיה די מאתגר להיות סטודנטית של מוטי שטיין. בוא נגיד את האמת, אבל אני חושבת שדבר נורא חשוב שמאפיין את מוטי, זה שהוא באמת הוציא מכל הסטודנטים שלו, ואני חושבת בכלל מכל מי שסבב אותו מבחינה מדעית ולא רק מדעית, את המקסימום. ואני חושבת שזו הסיבה שאני עומדת פה היום, והרבה זה בזכותו. קצת לספר על האתגר של להיות סטודנטית שלו, אז אנקדוטה קטנה, ממש קצרה. כידוע עשיתי את הדוקטורט בים המלח, לפני שזרקו אותי לתוך הים התיכון. נסענו, שטנו אל תעלת העודפים בסיל בין האגן הצפוני לאגן הדרומי, על איזושהי ספינה רעועה, לא הגדולה, הספינה הרעועה של מוטי גונן, אם אני לא טועה. זה היה קצת כמו לשוט לגיהנום, המים היו חמים, הזרימה הייתה חזקה, והמים היו אדומים גם.
זה היה בסירה.
כן, כן, אבל זה היה מאוד רעוע. בכל מקרה, באיזשהו שלב הגענו לסיל, ירדנו אל החוף, והדבר הראשון שאני ראיתי, חוץ מהדברים הבאמת היפהפיים שהיו שם, במיוחד כל מיני דיאפירים של מלח, זה היה מוקשים. מוקשים נגד אדם. הייתי מדריכה במדריכת חבלה בחיל הנדסה, אז ישר זיהיתי אותם. והתגובה ההגיונית היא כמובן ללכת אחורה ולחזור לסירה, ומוטי נעמד שם צוהל ומאושר והציע בוא נזרוק אבן לראות אם זה מתפוצץ. לשמחתי הרבה, אני חושבת שהמוץ ושמוליק היו איתנו, הם שכנעו אותו שזה לא ממש רעיון טוב, וככה נמנעה תקרית דיפלומטית. Okay, so I will move to English. That's okay. So I'm presenting here a work that Motti was involved in, and with all the other really amazing people that I had the opportunity to work with. But you can see from the names here that I changed from the Dead Sea and moved to the Mediterranean. And we see here Ahuva Almogi and Barak Herut. With Motti and Yudit Arlavan, we also measured the strontium and neodymium isotopes, and the work was performed by Tzafit Mor-Federman, who was my first student as a grown-up researcher. Okay? So I'm presenting the hydroclimatic controls on the Nile littoral cell development during the Holocene. We are concentrating on the continental shelf of Israel, and as it is downstream, the Nile Delta, of course, it is highly influenced by the climatic conditions and by the sources of material that is coming with the Nile. זה לא זה? גם לא?
זה ישר למחשב.
זה ישר למחשב, אוקיי. So I'll move that here.
מה עכבר?
אוקיי. Okay. It's okay. So we are looking here at the southeastern part of the Mediterranean, and the main question is what controls the development of the Nile littoral cell. And of course, the aim is to reconstruct the geological history of the development of the continental shelf. So you can see this is an old image that Ahuva Almogi gave me, I don't know, 20 years ago. She used it for her works in the Mediterranean. But you can see clearly that from the Nile Delta towards the Haifa Bay, this littoral zone is poor in carbonates. Okay? It is mostly controlled by the siliciclastic sediment that is arriving from the Nile. We are kind of used to it, and it is part of our childhood, but this condition is rare in the Mediterranean. It's unique to our region. And you can see it also in the map on your right, again, a map from a work by Ahuva, showing the increase of calcium carbonate in the sediments in the surface as we go towards the north. Okay, so as we go far away from the Nile Delta, the increase in carbonate in the sediment is increasing. So one main parameter is the distance from the Nile, okay? And it reflects the lithology in the continental shelf. Another main factor, of course, like always, is climate. We are looking here at two maps of the seasonal patterns over Africa, of the monsoonal rains that migrate in a south-north direction. So this movement of this climatic zone is highly influencing the amount of water that we have over the Nile watershed, and of course the Nile watershed is supplying the southeast Mediterranean both the water and the sediment that that are recording our record on the continental shelf. This one. Another important parameter to be aware of is the seasonal floods from the African monsoon that are flowing through the Nile. So we are looking at the hydrographic condition during a normal Nile flood regime. Of course, what do I mean normal? Of course, it's not the normal condition. It refers to the fact that today the Nile River is dammed by the Aswan Dam, and we are not receiving anymore the flash flood waters, runoff, that is loaded with fine suspension and nutrients into the Eastern Mediterranean. And these are two relatively old images or figures showing that condition. On your right, you can see pictures that were taken before the Aswan Dam was built, and these are flash flood plumes that we're used to seeing in the Dead Sea. We are seeing them here on the Eastern Mediterranean, bringing the fine suspension from the Nile seasonal floods. And it was also mapped by Earth in 1956, just before the dam was constructed. And you can see here the lines, the equal salinity lines, showing the plume of relatively not fresh, but less saline waters floating towards Haifa Bay. So that was shut down, but this is an important feature that gives us a hint of what was happening here before we disturbed the normal conditions. Another important thing that affects or controls what do we have in our continental shelf are the main sources of sediments. And we're looking at the geological map that was, of course, created by Motti and published in 2007. I changed a little bit the colors. Your colors were really exotic. And you can see here both the Saharan shields, the Arabian-Nubian shield, and the Blue Nile. So each of those geological features is contributing different sediments into the Nile River, which are being transported by the White Nile, by the Blue Nile, and by the Atbara River towards the delta of the Nile. So we will go back to that image later when we will talk about the isotopic signatures of those rocks. And what I plotted on Motti's map is the migration of the northmost extent of the monsoon rain band in the past 8,000 years. Okay, we are talking about that time period. This work is coming from that reference, and you can see that if today, at present, the monsoon belt is located here in the south, in the early Holocene, it was much to the north. Had the northern position. So this must be reflected in the sediments that are coming to the Nile littoral shelf. Another factor, the global sea level, in the past 8,000 years changed quite a lot. We are seeing the post-glacial, the end of the post-glacial sea level rise, and this is a graph showing the increase in sea level. This graph was taken from Lambach 2002, but Dorit Sivan, who is sitting here, also did quite a lot of work using index sea level elevations in the coast of Israel, reconstructing this curve. And you can see here an interesting map, of course, this imaginary map of the fan delta of the Nile, how it prograded and changed in relation to the sea level. So if 30 to 500,000 years ago it was exposed to the atmosphere, as sea level rose, it was flooded by sea level, and around 6,000, 8,000, 6,000, 4,000 years, there is a lot of accumulation of very coarse sand. The coarse sand that we see today in our coast is originating from this coastal zone in the Nile fan delta. Okay, so let's get to the study. We used two cores. that were extracted during the artificial island project somewhere in the 90s. Core V101 and core V115. One is representing the north, always in blue, and one the south, always in red. The water depth that what they were extracted from was around 35 meters, just after the sandy zone of the coast, so it is relatively fine-grained sediments. The length core is about is a little bit more than 7 meters. These cores were dated by radiocarbon. I'm not showing the dates here. And also I plotted here on this map the environment surrounding this course. So we are here to downstream or upstream the Nile Delta. We have the Sinai Negev dunes, the less soils that are also involved in this system. And you can see that we are located at the shelf edge, and I will in our work, we also correlated our results to different cores that were taken from the slope of the continental shelf. So this is the sedimentology, something that I really like, measuring grain size. I think grain size is a very, very basic parameter, but it gives us a lot of information. And you can see here the different cores in the south in red, and blue, the northern core, and you can see that they differ from each other. You can see in the southern core that we have a high content of sand at the last stage of the sea level rise, while in the north we see a lot of fluctuating grain size distribution. And as we pass the age of 6,000, 5,000 years ago, the amount of sand decreased dramatically. So this is a very distinct change in the sedimentological character of the sediments. We interpreted it as because it correlated with the sea level, we at the beginning thought it might represent the change in the positional environment, but more than that, when looking at the grain size and later also the geochemistry, we understood that we also have a transgression of that moved, recycled the transgressive sands from the Nile Delta towards our shore. Once the sea level stabilized, we stopped seeing it because the sea level is not eating anymore the fan delta of the Nile. Okay? In the northern core, which is located in a more narrow environment on the narrow shelf, we might see the dating resolution is not sufficient enough to try to correlate it with a specific climatic events, but we suspect that we are seeing increased storminess that is being seen in the Holocene record of the northern side. Okay, so now let's get to some geochemistry. We're looking at the total organic carbon, the calcium carbonate, and the delta C13 proxies in the two cores. Again, red is the south, blue is the north, and you can see that both of them are showing, as seen here, both of them are showing a big difference, a big change at the mid-Holocene, around 6,000, 5,000 years ago. And the way we interpret it, first of all, the calcium carbonate was higher at the beginning of the Holocene, and it decreased in the later Holocene, and we interpret that as seeing the fine suspension of Nile sediments arriving. So for some reason we had less fine-grained sediments, less siliciclastic sediments at the beginning of the Holocene. We see really nicely the Aswan Dam setup or construction and the increase in the calcium carbonate content because the siliciclastic sediments are being stopped by the Nile Dam. We also see that we have low productivity at the beginning of the Holocene, or at the 8,000 to 6,000 interval, and this is in contradiction of what we know on the African humid period that is also responsible for the development of the sapropel in the Mediterranean. And it was quite difficult to explain, but based on the foraminiferous species that Uva recognized there, we are certain that we are looking at oligotrophic conditions, while at the same time we have increase in the Nile flow. And the delta C13 organic matter signature presents a marine signature, and at the later part of the Holocene, it presents phytoplankton blooms. So again, while we had a lot of water coming during the African humid period, we didn't see it in the continental shelf, and only later, at the later part of the Holocene, we start to see phytoplankton blooms. The difference between the south and the north represents the distance from the Nile. When we were closer to the Nile, we see higher delta C13 because we see a better signature presenting the nutrients that are arriving. Okay, these are the geochemical compositions from those two cores. And I chose to present here a few proxies. We use the ratio iron to silicon to represent the weathering of the Ethiopian highlands basalts. Okay, calcium to aluminium and barium to aluminium represent the ratio between siliciclast and biogenic carbonates, and we also have ratios that represent heavy minerals and grain size proxies, and the elite clay mineralogy. Okay, that is a dust-bearing signature. It is coming with winds, and it represents changes in wind distribution and dust supply from the Sahara. Okay, so you can see here again, we see a very drastic change about 6,000 years ago. We see that there is an increase in the ratio of iron to silica at the end of the African humid period, and a decrease in the titanium and aluminium, barium to aluminium, calcium to aluminium ratios, and also in the heavy metals and the clay mineralogy proxies, we see a decrease. So all of those are representing a very big change that is happening about 6,000 years. Okay. So let's proceed to the interpretation of those records. So what we see here is that the transgressive coarse sand transport along the shelf, as I showed before, is seen here, a relative increase in the biogenic material due to the starvation in fines. And the reason for that is, although we are at the watershed receiving a lot of monsoonal rains, there is reduced erosion due to vegetation cover over the Ethiopian basalts. So we are seeing here at the continental shelf a sedimentological and geochemical evidence for the African humid period. While when we move to the late Holocene, we see the sea level stabilization and the increase in fines that are transported with the Nile seasonal floods, represented in the ratio of iron to silica. We see a decrease in precipitation over the Nile watershed and an increase in surface erosion and sediment contribution, and an increase in dust inputs in the last 3,000 years. So you can see there in a small black arrow the signification of how can we detect this aridity, an increase in aridity and the increase in dust. And this dust was also detected by other works by Motti from caves spertums and in a work that we recently published in the Dead Sea. Local streams versus the Nile. So what we see that in the early Holocene, there is a signature. We can see here the end members of the local streams at the bottom and the Nile sediments at the top. We can see that in both cores, the geochemistry, the iron to aluminium ratios show a distinct change at the middle of the Holocene. And during the early Holocene, the sediments from the shelf resemble the local streams, and in the later, more arid period, we start to see the Nilotic sediments. And again, this was really an interesting observation, very new, but it was probably related to the fact that during the late Holocene, because there is a reduction in rain and vegetation over the Nile watershed, we start to see the influence of erosion and transport of fine-grained sediments. And my last and very important proxy was strontium to neodymium isotope ratios. And you can see here also both for the neodymium and the epsilon neodymium and the strontium isotopes, a big change that is happening about 6,000 years, representing the change in the source of the sediment. You can also see here at the last 3,000 years that in the northern core we are starting to see a more dusty end member that is reflected also in the marine environment, although it is always said that in the continental shelf it's almost impossible to see the dust contribution. Still, it was significant enough so we can see it. And my last result slide is the neodymium to strontium radioisotope fields that represent the hydroclimatic implications. You can see here in yellow the fields of the ratios from both cores together, which correlate. And you can see that somewhere around 8.5 to 8.1 kiloyears before present, we have our field is located somewhere between the Sahara granatoids and the trital calcite and resemble the mountain top less in the Negev. Although we only have only 3 points, we interpret that as the 8.2 northern hemisphere cooling event that was recognized in deep cores in the Mediterranean, and we believe that we also see it on the continental shelf. Then we have a period between 8 to 5.5 kiloyears where we see dust that accumulated previously in the LGM that was remobilized by fluvial processes due to the increase in precipitation during the African period. So, and in the last 5.5 kiloyears, we see sediments that are derived from the Ethiopian highlands and the Nile sediments. So I will summarize that the treated sediments were mobilized to the continental shelf mainly by the Nile River, but also from small local rivers. During the deposition of Sapropel 1, the Nile littoral shelf was characterized by oligotrophic conditions and deposition of transgressive deltaic sands. During the early Holocene, dust that accumulated in the surrounding desert during previous arid periods was remobilized by wetter conditions of the African humid period. During this period, the vegetation cover over the Ethiopian highlands was inhibiting removal of basaltic salts at the Blue Nile headwaters. And in the last 5.5 kilo years, a distinct mud belt was deposited with increased contribution from the Blue Nile basaltic sources. These are the fine-grained sediments that we see in the southern core. And in the past 3,000 years, we have the aridification of the Levant, and we see a higher contribution of dust. Thank you.
Okay, so the next one is the hero from Weizmann Institute, who actually got crossed with Motti during their postdoc already, working on the Dead Sea deep core. Did quite a nice work on the salts there and on the sediments. Okay, יעל קירו from Weizmann Institute. Can you hear me? יעל קירו from Weizmann Institute. She crossed Motti only during her postdoc, but still did very extensive work on the deep core, which Steve talked about, and she's keeping on doing this work. This time, she will give us her lecture about her work now.
רשום שזה תרמית. עדי, it doesn't work.
בסדר? HDMI. חובר ה-HDMI?
כן. לא, זה יצא... עכשיו זה צריך להיות בסדר. סיפלי? הנה. סיפלי.
מופיע.
מעולה, כתוב לי גם זמן.
אוקיי.
So good morning, everyone. Or we are already afternoon, so I will try to, I know we have a delay, I will try to speak really fast. So, you can't hear me? למה לא שומעים? רגע. עכשיו שומעים? שנייה, אני אנסה לשים את זה קרוב יותר. Now you hear me? לא נוח. Okay. Do you hear me? Yes. Okay. So this is the laser. Okay. So, Motti, happy birthday. And thank you for being a great and inspiring teacher and mentor. So I'm not presenting here today a work that I have done with Motti, but a lot of things that I do is inspired by many years that I know Motti. So I'm talking today about a work that I've been doing in the past couple of years about the potential role of coastal aquifers in ocean chemistry. Sorry. I'm working with a bunch of colleagues, students and postdocs that you can see here in several places. So the big question that I'm motivated by is what dictates ocean chemistry. And you can see here all the known sources and sinks that control ocean chemistry. But while the role of rivers and mid-ocean ridges established decades ago, the role of submarine groundwater discharge, which we also call SGD, is often overlooked in the context of ocean chemistry. And trying to understand the fluxes that are coming through SGD may close significant gaps about what we know in ocean chemistry. So the main problem in quantifying fluxes of SGD is that we don't know exactly what the actual element flux is. It is acknowledged that SGD is significant to the chemistry of the ocean. There are several studies that show that the water is modified. It controls several element systems and isotope systems. But we don't know what are the actual fluxes because it's hard to identify the concentration of the end members because the groundwater flow in coastal aquifers is very complicated. Okay. So submarine groundwater discharge includes all water that flows from the land into the sea and underground. It includes both fresh terrestrial water and salt water. And it also is acknowledged that most of SGD is salt water. But when we are talking about salt water, we are talking about this very, very complex system. So the saltwater fluxes from the aquifer into the sea include several circulation mechanisms that are driven by different spatial and temporal scales. So it includes small-scale processes that are driven by tides and waves and cause this small-scale circulation or tidal pumping. It goes through seasonal circulation that is driven by the change of sea level or water table, and it includes also the long-term process of this big number one arrow here that is driven by dispersive mixing and density differences. And in order to know what exactly we are measuring here when we are studying SGD, it is and if we want to quantify the actual solute fluxes, it is crucial to distinguish between the fluxes of each one of these processes. So I'm trying to focus on the long-term seawater circulation, which is a density-dependent dispersive circulation that you can see here because of its greater potential to be modified by water-rock interaction and actually affect major elements in the ocean. So this is what we currently know about different fluxes into the ocean. This is the amount, this is the flux of river. These numbers are well established and known. When we're talking about fresh water, and I mentioned it also before, we're talking about the estimates are 0.1 to a few percent of the river discharge. And there are total SGD estimates that you can see here that are about 3 times or between 2 to 3 times of the river discharge. And again, this includes mainly the saltwater fluxes, not freshwater fluxes. And we don't have a lot of estimates or breakout of this total SGD and the different fluxes of the different mechanisms. And we have maybe an estimate that I've done in my PhD years ago of that is about 10 to 20% of the river discharge. But again, this is in the Dead Sea, and I would like to try to estimate this number in the ocean. So my main goal is try to establish a field-based method to identify and quantify the long-term circulation process and to say something about element fluxes into the ocean. And the way that I'm trying to do it is using a very typical behavior of groundwater in coastal aquifers. This is data from Moritz Ivan's work a while ago, where what we see here is that the coastal aquifer groundwater is enriched in strontium and calcium and depleted in potassium. You can see here the conservative mixing line with seawater, concentration of strontium and calcium versus chloride, which is conservative, and the concentration of potassium versus chloride. And this behavior is very typical to coastal aquifers and is usually seen inland and not on the shoreline water. So if we see it further away from the shore, we can assume that it is reflecting longer-term processes and the flux of the long-term process. And I think what I'm showing further on will also prove that this is what we actually see, and that the effect on the composition of the water takes a while and does not reflect the short-term processes. And you can see here, so what I've shown is a very typical behavior of coastal aquifers, but there are numerous of water-rock interaction processes in coastal aquifers that are summarized here and are affecting the major elements of the aquifer. So what we're trying to understand is, so we can use, first of all, the modified water in order to distinguish long-term fluxes, the long-term component fluxes. But also this suggests that if these fluxes are large enough, then they can actually affect the chemistry of the ocean. I'm showing today some results from Indian River Bay in Delaware, and from here, from the Eastern Mediterranean, from Nitsanim. And I will start from Indian River Bay, where we had this array of seepage meters and piezometers. And this is in this area, it's a very typical settings for the typical transition zone in coastal aquifers, setting where you have fresh water that flows above salt water in the transition zone. And when we are looking on potassium versus strontium, we can see here that most of and this water is collected from here, from the shoreline. It's not further inland. And the idea is to try to find in these waters if we see any long-term component. So what we see here, that most of the water is lying on the conservative mixing line, reflecting the short-term component, but we have some samples that are enriched in strontium. This is strontium versus potassium, just to highlight the water that are different from the other that went through water rock interaction and got enriched in strontium and depleted in potassium. And you can see here that there are a few samples that are a bit different. So we can look at these samples at a spatial context and maybe say something and try to think if it's arbitrary or it has any kind of sense about the location of where we found the samples. And I think this is pretty exciting because what we see here is the fresh saline transition zone. This is the fresh water is blue and the salt water is red, and this is a cross section of the field study that you can see here. And all of the samples that I showed before that are diverted from the conservative mixing line, they are here, and they flow along the fresh saline transition zone. So this strengthened this hypothesis that the enriched samples are reflecting a specific flux of the long-term flux, component flux. So this is another view. Again, this is a cross-section, the same cross-section. You can see here in white the fresh saline transition zone. These are chloride contours, and this is strontium concentration that is reflected by percentage of enrichment. And again, you can see here that it's not arbitrarily distributed. You can see here a long-term circulation cell and some shorter-term circulation cells. Here the strontium and the composition of the water is very similar to seawater. So definitely we didn't get a lot of water rock interactions here. And then we can go further on and calculate the budget and calculate the actual flux from what we know and what we know from the end members. So I won't get into it too much, just it's a very simple mass balance, estimating here the end member from the literature. And again, this number has probably 50% uncertainty, so currently we need to do more studies in order to constrain the end member, but still we can calculate the relative flux of the long-term component, which here is calculated to be, in the case of Delaware, it is calculated to be 12%. So we can see that most of the water discharging is this short-term component. This is expected. And this 10% maybe looks a little bit, but if we are taking the amount of enrichment or depletion of minerals, this is actually significant and important and affecting the chemistry of the ocean. So of course, if we have the total fluxes from the seepage meters, we can translate this relative flux into a total flux. But I want to move on here and to show what we have from Nitzanim. So most of you probably know where it is. And in Nitzanim, there is a very good settings to study the salt water through a flow path from the sea into the aquifer. There are a bunch of wells that are perpendicular to the shoreline. And again, here we see the expected behavior of enrichment in strontium and calcium and depletion in potassium. We also measured uranium in this case, also measured isotopes, which I show because it's Moti's birthday. So what we see here it is very typical, but we did look at it in the context of the location of the different wells. And what you can see here, that close to the shore, in the close wells that is closer to the beach, the enrichment is not as significant as further away from the shore. And also what we can see here, that the enrichment in uranium is much faster than the enrichment in strontium. So by using the rate of enrichment or depletion, or using several elements or isotope systems, then we can even get more information that can help us to distinguish between the water bodies and the rate of water rock interaction and the different components of the different temporal scales of circulation. So we can use, I found that it's easy to use uranium versus strontium in order to try to distinguish between the different water bodies. And this is a cross-section from Nitzanim, and forgot to write here the credit, but the ages here are from Itai Reznik and Yossi Yechieli's recent publication. So here we're very lucky because we have the ages, and what they found is that the groundwater, the salt groundwater that is close to the sea, they are relatively young, and then when they flow further inland, their age is increasing. So we actually have here ages of groundwater, and we can look at the composition of the groundwater in the context of their age. And what we can see here in the young salt water, the star here is the composition of seawater. You see that the water is very similar to seawater, and they are not very modified. And then when we go further inland, we get higher enrichment of uranium and strontium. And then that the water is flowing here is the transition zone. They are mixing with fresh water. They are flowing back to the sea, and they are enriched in uranium and strontium. And this is very important observation, because when we're talking about the fluxes, we want to know that the actual modified groundwater is flowing back to the sea, and this is what we see here. So the water here in the transition zone is not a mixture of what we see below here. They went through this whole circulation and then flowed back. So this is the effect that we can see on ocean chemistry. And I promised isotopes, so we have here strontium isotopes and uranium isotopes. And this is mainly, I think, isotope exchange, but we see that the composition of seawater, of uranium and of strontium, and how it is decreasing and increasing with distance from the shore. Also here, the increase in the uranium isotopic composition is faster than the decrease in the strontium isotopic composition. And again, this is another tool that we can use in order to identify specific components of fluxes of seawater from the aquifer into the sea. And also we can calculate the rate of change and fit curves and kinetic rates that can give us more quantified information. I want to finish here with a little bit of modeling that Yuda Levy, who is working with me as a postdoc, was doing. So again, here in purple is the freshwater and saltwater. These are simulation, and what we're trying to do here is to simulate all processes together and try to then break the different processes and calculate the relative fluxes theoretically. And also in the model, what we see here that in the a small circulation cell that is driven by tides and the waves, we see large fluxes, but small residence time, and in the large density dependent driven circulation, we see small fluxes and but longer residence time. And the idea is to try and test different parameters, different environmental and hydrological parameters, and see how they are affecting the relative fluxes and total fluxes. And we can see that the different parameters are affecting differently, so then we can extrapolate it globally and try to give this estimate of how much the different fluxes through the different processes are affecting or have the potential to affect the chemistry. Here we see that the long-term seawater circulation is about a few percent from the total discharge. It's a bit lower from what we calculated, but we are still working on it, and I think that maybe the dispersivity should be higher in order to explain the results. So I just want to finish here with some global budgets, or this mainly gives me a motivation to keep and investigate this issue and to show you that there is a potential in terms of the budget to actually affect the chemistry. So these budgets took into account only rivers and the mid-ocean region hydrothermal fluxes, and calculate the flux of the long-term component as the missing component, while taking the known n members. And from the literature, again, it has a large uncertainty, but I was very happy to find that according to the calcium budget, the potassium budget, and the strontium budget, we reached very similar values of a few percent. And again, this few percent, for example, for calcium, reach the same order of magnitude of the contribution of rivers. So I want to just finish here with the summary that we can use measure and trace elements in order to try to distinguish specific components of SGD, and we can use it in order to quantify globally fluxes of seawater circulation, long-term seawater circulation to the aquifer. So thank you very much.
Thank you. And now we move to Yossi Echieli from the Geological Survey. And he is a long-term colleague with Motti, and they work quite a bit also on together as advisors of students on the Dead Sea and on groundwater of the Dead Sea. סטארי, אתה לא שומע מפה, אה? Okay, Yossi. Go ahead.
All right, here we are. יום הולדת שמח, מוטי. Happy birthday. I will talk about a new tool of radioactive noble gases for dating groundwater. And I will give talk a bit about the introduction of this tool, and then a little bit about examples, the last of which is the one that we did together with Motti. And right? Okay, so these are the main tools that we use in groundwater. For many years, we used the C14. Which one? How do I go? No. Up. Sorry, can you say? לסרקן, אוקיי. אוקיי. אתה רוצה את זה? אני לא יודע אם זה עובד, אבל לא חשוב. תתחיל, אני אעשה. Okay, so the main tools that we've been using for many years were radiocarbon and tritium. And the new ones are the argon, and mostly that we're talking about is Krypton 81. As you see, this one kind of fill in between those two tools that we've been using in groundwater, and this one is a new tool that enlarge our capability to date. Okay. So, and why noble gases are important and good for our case is mainly because we are talking about they are conservative. There's no interaction with the aquifer's rock, and for those of us who know how it is to date groundwater with radiocarbon and all the corrections that you need to make, it kind of makes it much easier to be able to assume conservative. We'll go on to this. So the way we go in the field, we take this equipment into the field, and we put in we hooked in the well, and we take the water into this device, and we extract gases, and we put all of that in the container, and all we need to bring it home from the field is this container, while years ago you had to take several cubic meters of water, and therefore it was very difficult to use this method. And this new method of measurement it's called ATA, it's atom trap trace analysis, and this has been used and developed in the last 20 years, and it's still being developed. So as I said, I will talk about a few examples. The first one will be from the Nubian sandstone aquifer in the Negev. It's part of the PhD for Iran, with many partners, some of which are hydrologists, others are the actual people that do the measurement in the lab. So the aquifer that we are talking about, for us, it's a huge aquifer in the Israeli standards, but as you see, it's much smaller than large aquifers in Northern Africa and the Middle East. And this is the aquifer that we are talking about. It starts from Sinai, in southern Sinai. It goes into the middle of Sinai, and then it goes west and east. Of course, we are interested in that part. It goes into the Negev Desert and toward north, Dead Sea, and the south, the Red Sea. So the samples that were taken mostly, there is groundwater wells, so it's mostly between the Red Sea and the Dead Sea. Oops, sorry. Just a minute. Sorry about that. Okay, so this aquifer was dealt with quite many times in the past, and most of the work related to groundwater dating was done with radiocarbon, which was the main tool up until very recently. And what you see is that the ages that they were obtained, were mostly between 25 to 30,000, and this already was noticed that it's very close to the limitation of radiocarbon. This was one of the main motivation to go into these new tools, and indeed, what you see the ages with the Krypton 81 are completely different, between about 50 to about 5 to 600,000. So these are the ages that were obtained, and again, this was done pushing the limitation very far, and these are the real one. Also, looking at this one, you can see that it's not a simple age evolution. There are different ages, and the reason is that there's recharge that coming from far away, what you saw before from Sinai, and there are recharge that is coming from the main Machteshim, the three of them, and this put in new water. And indeed, when we look at the ages versus, for instance, O18, we see that there are at least two sources, one of which is young and less depleted, and other one which is old and much more depleted water. So we are talking about at least two main end members, components, with different origin in terms of time, location, and climatic condition. One of the ways to check whether this method is actually working was to look at the place where there are three wells very near each other, and to see whether we get younger ages at the top and older, and as we expect as hydrologists. Indeed, we see that the one that is very in the middle, which is the shallow one, we get very young water and middle age, and the one that is at the lower part, deep part, we get older, all in 420,000 years. The last part of this aquifer that I want to talk about is in the southern part, is the one that this flow path going toward the Red Sea. What we expect to have here is old water coming from the Sinai, and younger water coming from the Edom Mountain, Jordan. And the results were indeed showing, first of all, that there's a mixture between depleted and less depleted water, and the ages also goes well with those mixtures. Okay, so the second part of my talk is a second example. It was about age of seawater intrusion into the aquifer and the mountain aquifer, and Judea Mountain aquifer, and the reason the age is actually we want to know because we want to understand the connection with the sea. It's important. First of all, it's a long debated scientific question. People have given different ages, starting from very recent to Neogen water or even older. So and it also has a practical aspect, which is the salinization. If it's all groundwater not connected to the sea, there is a lower risk. If we pump a lot, there's a lower risk of salinization. If it's young water still connected to the sea, the pumping is of higher risk. This work, as the same as the other one, was funded by the BSF and also by the Israeli Water Authority. So the aquifer that we talk about is the mountain aquifer, recharge here, and we are talking about the part that going west. It turns out that when you go with water toward the sea, there is a fast change that block that water going farther west to the sea. It goes from permeable to impermeable layers, and therefore the water cannot go all the way to the sea. So the connection with the sea is debatable. Still, we see in the northern part of the aquifer, we see quite many locations with saline water, almost with the salinity of the seawater, and quite similar in many parameters of the chemistry. And as I said, few people, like Uri Kafri said that it's recent seawater, and most people would argue that it's all the water, some of the neogen, and even older. So when we started this work, any age would be correct. We had no idea what could be the real age of this water. And in this case, we use two noble gases parameters. One was the argon-39, and the other one that was krypton-81. And for each one of them, we built an equation that shows the main processes. Some of these we know very well, others we assume. And what we actually wanted to know is the TS and TF, which are the time, the age of saline water and the age of fresh water. And this was put in a graph like this. I will not go into all of that, but the blue part is actually the possible ages coming from these processes. And for example, if we look at the Bet Eliezer sample, then we see that the possible ages are between 13 to 40. And if we look at another one, the ages are younger than about 9,000 or something like this. This is also seen in this picture. Now, if you put it on a map, if you look at this map, these are the 5 samples that I talked about. We see there's no increase in ages if you go from north to south. I stress this point because some people said that saline water come from the sea going into the aquifer and then going south. So there's no argument for that. Maybe there is some older water as you go east, but I wouldn't go too far about that as well. There's more data now that in the following project by Itai Resnick that shows more or less the same young ages, suggested, as I said, by Kafri. And just recently there was a study by Isha and Weinstein that shows from radium isotopes that also low ratios, much lower than secular equilibrium, indicating that we are talking about young ages of the same groundwater, for most of the same groundwater. So if we put all of that together, then it seems like there is some intrusion from the sea into the aquifer. You can even calculate more or less the rate of that intrusion, which is, for hydrology purposes, seems quite reasonable, but we are not sure about it. And if you want to learn about this aquifer, you actually need to do it in a 3D kind of modeling, because this is not the only way saline water can go in. But if it does, it can go through some erosional channels, faults, facial changes we are not aware of. Okay, so the last example is the one that Moti Shtein, the hero of the day, is part of. And this was done by the part of the PhD of Nurit Weber. And it's a small part of a study that I will want to elaborate a little bit just about the age part of it. So again, we want to know the age of the saline groundwater of Enschede mostly, and I will talk only about this part of the groundwater dating with radioactive isotopes. So we managed to drill, because if you're dealing with noble gases, you cannot take just a sample from a spring. It's too much of air connected with the air, with the atmosphere, and therefore we drilled a well very near the Kedem springs, and we did radiocarbon and krypton-81, and as you see, they more or less agree of say 25 to 30,000 years, and if you put that on the lake level chart, then you see that it fits quite well to the time that the lake level, the Nissan level, was high, much higher than today, about 200 meters higher than what it is today. And if you're looking for an hydrological model, then at the time that there is a high lake level, the water of the lake go from where there is a high hydraulic head from the lake itself, and they go into the adjacent aquifer, and this is where the brine comes from. And when the level goes down, then we see that the head of the water, of the groundwater, the aquifer, is higher, and therefore the water from the aquifer and from the brine is going back to that sea, and you can summarize it this way, that at the time, about 30,000 years ago, there was a high lake level, and therefore there was infiltration of the brine into the marginal aquifers. And at the other time, like today, there is the lower lake level, and then there is a discharge into the lake of that brine. So this is the source of the brine that we all know in the Kedem area going into the Dead Sea. So just to summarize, we see that radioactive noble gases enable us to have a better dating. It's a new method of sampling and analysis that allows a more accurate result and much more samples to be taken. In the Kurnov aquifer, we see that there's much older than we previously thought by radiocarbon ages, and there's actually water come from the Sinai older, and with the local recharge of younger water, and therefore we have mixing of several sources. And once we will know better the ages, this can serve as an archive for paleo-temperature and paleohydrology for the last 500,000 years, if you want. The saline water that we use two parameters, and therefore it allows us to have a separate age estimation of fresh and saline groundwater bodies. And we see that it is much younger than most people previously thought. And we would need a new 3D hydrological model in order to understand it. The Kedem brine is originated from the Lisan Lake at times of high stand, some 30,000 years ago. And its source, according to the chemistry that I didn't talk about, its source is the upper part of the lake. And we are now, there's a following work by Tai Resnick and the Chinese partner. They do the analysis to get a better resolution and to improve, by improving the analytical methods. And that will allow us to do a better record of paleoclimate research. Thank you very much.
Okay, so we can go out for lunch and reconvene here at 1:30. Yeah.
מה הגיל של DC?
של?
DC.
פיזי? אף אחד לא עושה שם קריפטון עדיין. יש לי כל מיני הצעות מחקר על העניין הזה, אבל לא. הם עשו פחמן 14.
זה קרוב ל-200,000?
אני מתאר לעצמי שיכול להיות שיש שם מיליון, יכול להיות שיש שם יותר.
תודה יוסי.
בסדר, אתה ביקשת ניטור?
לא, מעולה. באמת, לא נשמעתי...
לא, נראתי.
לא היה כיפה.
האמת היא שדוקטור הדוקטור היום משתמשים בזה. לא מעט.
כן, אני יודע. והאמת היא שאני הסתכלתי על זה ופתאום אני קורא, תגיד, איכשהו מהשיחות איתו אפשר אף פעם לדעת מה קורה. אז אתה אומר שהגיל שלי מקדם הוא ליסני. בעצם זה גם מה שהמודל של הכבשים, של הגופים, ראה את אותם דברים, נכון?
זה גם מה שההידרולוגיה אמרה קודם.
אתה רוצה את העט האדום? כי התחלתי עם אדום. ותשאיר לי את החתכים הסכמטיים אם אתה לא מגיע אליהם.
בסדר.
אבל נראה שנעשה את זה, בסדר?
סל שלום.
מפתחות בפנים. אנחנו, יכול להיות ששבוע הבא, סוף שבוע אני רואה אותך.
אתם באים אליו?
יש לי כול.
אז תגיד, סוף שבוע הבא, לא יודע אם יהיה, אבל קשור, בכל מקרה.
אני מגיע לעניין הזה לא תהיה.
לא מודיע בזה.
טוב, יש לך את האדום פה, תסתכל על זה, דבר איתי, תשאיר לי עוד משהו, בסדר?
בסדר, נחשוב עליך.
אתה זוכר את הדיונים שהיה אינסופיים עם מוטי בהתחלה, שמפלס גבוה, מפלס...
ספר לי, מודל גולדשמיט, מודל זה. אני יודע.
אני חושב שזה מתכנס, וגם מוטי מתכנס בזה שזה...
זה שמוטי מתכנס זה נס. אבל בסדר.
זה כלי, תשמע, זה כלי חדש מעניין.
כן, כן, אני... טוב, יש לי עבר בגזים אציליים.
כן, אנחנו דרך אגב גם רוצים... יש הרבה נתונים של איליום.
אני שלחתי לך את זה, לא? מרטין סטול. אתה יודע מה זה? אז לא אני נתתי...
לא זוכר.
נתתי לאחד מכם, לדעתי אני נתתי לך...
העבודה שהוא עושה...
מרטין סטוד, הייתה איזו תלמידה שהוא שלח, עבדה עם אביבור, איתך? לא, לא איתך, עם אביבור. עם איתי אולי, או רק אביבור.
יכול להיות שגם איתי.
לא משנה, זה לא העניין, אבל יש שם מלא דאטה נורא מעניין.
יש.
טוב, זה מזמן.
לא מלא.
גם אני סימין.
יש, רואי רק שעושה הרבה יותר, ועכשיו הוא מנסה לעשות עבודה גם מהסוג שאתה בעצם עשית. הגרענים.
כן, כן.
בטח יראה מעטפת.
טוב, אחלה, אז
יש הרבה נתונים.
כן, אז כן, מעניין מאוד. טוב.
ניסיתי לדחוף את מוטי בכל זאת, אבל...
לא, האמת שאני דווקא בעד, האמת שזה מזכיר...
עשית שאני קצת...
לא רציתי יידישקייט, כי יש יותר מדי יידישקייט, אז אני בעצמי עכשיו מוריד, יש לי שקופית אחת של יידישקייט ואני רואה אותה.
אתה מדבר תכלס על הפרויקט שלך?
כן, כי אני חושב שהקהל עייף מזה.
במידה מסוימת זה נחמד.
כן, עד גבול מסוים.
אבל בסדר.
כן,
לא יודע.
בסדר, בואי נסדר את זה. והכי חשוב לראות אם הווליום עובד.
עכשיו.
זה יש לי. יש לך גם כאן, אז לא צריך. זהו בעצם. אהלן, גברת.
מזל טוב. איזה כיף.
היא הייתה סטודנטית שלי. שלי ושל יגאל.
כן.
רות רבי. R-Square.
R-Square.
אז רק שנייה, אני רק צריך לשים משהו ואז אני...
טוב, אני פה בחוץ. בוא נחבר קודם כל את המחשב.
שנייה אחת, מה את רוצה, לכבות?
לחבר? למה לכבות?
אוקיי, בוא נסגור את כל זה. נשים את המצגת. מצגת קצרה. 5 דקות. זהו, עכשיו תחבר.
זה מה שאתה צריך לעשות. בוא ניקח את זה. חבר את זה.
איך את יודעת שהרמקול עובד?
נחיה ונראה.
רגע, בואו נפעיל את זה רגע.
בוא, תפעיל את המצגת. הרמקול עובד.
זה לא הראשון.
אני אראה, אולי אני אצטרך להביא לך...
אוקיי, עכשיו היא עובדת. היא עובדת, זה עובד.
יש הרמה של חבר'ה.
עובד, נגמר. הכל בסדר, אז אני משאיר את זה כאן.
וואי.
בסדר? תראי מה זה, רק נגעת בזה. מה עשית אבל?
לא לדאוג, אתה בסוף.
זה בסוף, כן.
איך קוראים לו? עדי יודע גם.
תראה, ראית מה הצלחתי לעשות? להביא את המשפחה שלך לשעבר לכאן, אחרי שלא ראיתי אותה. אני אומר, בסדר גודל של מתי עברת לכפר סבא? 99. בוא נגיד 2000. אני
חייבנו של 3, אבל יש לו זמן להבאה. הוא התחיל
בסדר?
כן, שמתי, אני רק אציע את ה-USB, לדעתי יאיר רותם.
יאיר, אתה רואה אותנו?
אני רק רוצה לסגור אותו, להוציא את ה-USB.
עכשיו זה,
כן.
זה יעבוד עם זה פה.
למה? אני תמיד בלחץ לפני ההרצאות האלה. תיאבון.
יאיר, אתה רואה אותנו?
נראה לי הוא לא שומע אותנו.
יאיר, בתיאבון. אתה רוצה לעשות בדיקה של המצגת שלך, או שאתה סומך על אבינו שבשמיים?
הוא בארץ, הוא בים.
אבל אתה במיוט.
אני לא סומך על אף אחד, אז בואו ננסה.
טוב מאוד.
רגע. שנייה. נתחיל את הכל.
מה השעה אצלך?
מוקדם, 6:20 בבוקר.
לא כזה מוקדם.
כן, רק שזה רק טמפרטורה 0 בחול. אבל זה בסדר, לא נסע באופניים. בואו נעשה את זה. לא נורא.
או.
אוקיי, אפשר להשאיר את כך, ואז יהיה...
כן, אז זה בסדר. מצוין. יכול להיות שאנחנו נתחיל כמה דקות מוקדם יותר, אבל אתה שם כבר מנשנש, אז אין בעיה, נכון? מעולה.
אני מנשנש, ואם אני לא פה תתחילו בלעדיי.
כן.
משהו אחר, איך זה בינתיים, הכל בסדר?
כן, החבר'ה מרוצים, מוטי מאוד מרוצה, אז בשביל זה אנחנו כאן בסך הכל.
אוקיי, טוב, צריך לעשות אנשים מרוצים.
כן. אתה לא רואה אותי אפילו בעצם. הנה אני.
אני אותך לא רואה.
הנה, עכשיו אתה רואה.
למה אני לא רואה אותך? אז רגע, זה מוצג במסך, ואיפה זה? באיזה חדר אתם?
זה באולם 109, הגדול.
הגדול, אוקיי. כמה אנשים שם?
אני לא יודע בדיוק, אבל בוא נגיד, on and off, 100, 90, משהו כזה. כן, משהו כזה. זהו. טוב, אז אני משאיר אותך כאן רגע, והולך לכבות שריפה אחרת.
תשאיר את המסך, אני לא מעניין.
בסדר, אוקיי. האמת היא שבעצם מעיין יהודאי, תגיד כמה מילים. הנה, יוחנן הצטרף.
יוחי, אמרתי לו לקום מוקדם גם כן.
כן, אבל יוחנן, אתה במיוט. אז מעיין יהודאי תגיד כמה מילים, אז בכל זאת המצגת שלך לא תהיה ברקע כרגע.
אין בעיה.
הנה, בוא נראה אם הוא עונה לנו.
אוקיי.
היי יוחנן. בוקר טוב. הנה, אני אגיד לך שלום עכשיו. אתה רואה אותי? אותנו?
אני רואה את המצגת, אני רואה את יאיר.
אז רגע, אז יאיר, אולי תעשה אנשר שנייה? בסדר. אז יוחנן, אתה רואה את המסך אבל? אותי אתה רואה עכשיו?
כן. הנה אתה.
בסדר. אהלן. אז הזום דולק, אתם יכולים להקשיב, זאת אומרת, יוחנן, אתה תקשיב, אם תרצה, להרצאות שמתקיימות. אם אתה רוצה לבדוק עכשיו את המצגת, גם אפשר. אבל סך הכל זה הלך לנו די חלק עכשיו, אז נראה לי שזה בסדר. בסדר?
השמש מתחילה לזרוח. לא, מוקדם קצת. לא, אני בלמון.
אתה בעבודה כבר?
כן. ירדנו לכאן, נסתדר כאן דברים.
חרוץ.
אני מאוד חרוץ, לא נסעתי הבוקר, נסעתי אתמול.
טוב. בזמן ההרצאות רק תעשו מיוט כמובן, שלא ישמעו אתכם משתעלים. ההרצאות של האחרים, כן? בסדר, אז אני רגע נוטש אתכם, אני עוד מעט חוזר. ביי.
יופי, תודה רבה. מה נשמע יאיר? הכל טוב, הכל בסדר, קר בחוץ עכשיו. נורא קר. אני האמת שעכשיו, השנה גם נוסע באופניים בבוקר, אבל אני חושב שזה צריך לעלות מעל ה-40, בשביל לצאת. אבל זה נורא עניין, אבל חוץ מזה הכל בסדר, אני יודע. לא זזנו לשום מקום, כל מה שאני עושה.
אנחנו מתכננים להגיע לישראל בינואר.
בינואר, אני חשבתי גם כן, אני צריך לתכנן. האמת שאני ברזרבה לאנטארקטיקה, לא נראה לי שזה יקרה, בהתחלה לא רציתי, אז עשיתי את הבדיקות, ואז גיליתי שהפספורט שלי פג, האמריקאי. אז הייתי צריך. אבל קיבלתי שבשביל כמה מאות דולרים אפשר לקבל את זה מהר. אז כן, אולי ניסה לארץ, לא יודע, לא הייתי הרבה זמן.
שנתיים,
כן, משהו כזה,
אני לפני שנתיים, היה לי, היום לנו, בגינה בלי תוכנית, לבוא לארץ, שחק לנסוע לווינה, ל-EGU, והכרטיסים עוד נשארו מאז.
אבל אנחנו בצרפת, זהו לא, אני לא עליתי על מטוס מאז.
ב-11 שעות גם אני יושב בלי מסכה, אבל רוצים לראות את המשפחה.
כן, לא, אני חושב לפני שנה קיבלתי את הבוסטר, כמעט הרג אותי, אז זה טוב.
כן, אמרתי שאנשים, אני לא קיבלתי את הבוסטר.
אני קיבלתי את הבוסטר, וזה היה כמו 24-36 שעות של שפעת. אבל זה טוב, זה אומר שהמערכת העיון, והאמת שעשיתי מיד אחרי זה, יומיים אחרי זה בדיקות דם, בשביל הבדיקות לאנטארקטיקה, וראיתי את המערכת האימיונית, הפרוטאין, בום, ספייק בצורה, אז זה בסדר, אני מרגיש טוב שלפחות היה אפקט.
טוב.
זהו, אני יודע. אני כל יום בעבודה, אנחנו... צערי הרב יותר מדי.
לא, אני בפנסיה, אני לא...
אתה בפנסיה. אני לא, אבל אני באמת שאני...
שלום.
גברת מעיין.
אני לא יודעת לאן להסתכל. היי.
אני לא יודעת לאן להסתכל.
אני כאילו עושה שלום במחשב. אני לא רואה איפה המצלמה. מה נשמע? יאיר ויוחנן.
בסדר, מה שאת אומרת. הכל טוב.
איזה כיף לראות אתכם.
עדיין בגרמניה.
אני בגרמניה, כן. טוב, אנשים מתחילים להיכנס, אז...
טוב, בואו נשתיק, נדבר. יאיר, בואו נדבר פעם.
בואו, כן, גם... בסדר, קרוב.
אוקיי.
הוא שומע אותנו?
בהצלחה, להתראות.
אתה שומע אותנו, יאיר?
אני לא חושבת שהוא שומע, אתה צריך לעמוד פה, יהודה.
אנחנו שומעים הכל.
שומע אותנו, יאיר? אם אני אצעק, אתה נשמע אותנו? רוזנטל! יאיר!
כן, כן.
שומע?
שומע.
תראו את מי רואים פה. אלוף ניחושי הטוטו. יאיר!
אני מקשיב.
זה שלך.
כן, כן. הבת שלי חושבת שאתה מגיע.
כן, הבת שלי מארגנת משהו, הבנות.
טוב.
יש לך רמקול, עיון?
כן, רמקול, נכון.
קשה, אם הוא פה הוא עובד.
מי זה החתיך הזה?
אתה מדבר עליי?
מוטי, שב.
תראה, הוא נראה כמו פרופסור.
מעלות.
מעיין, את מתחילה. זהו? אמיר, זה כל מי שהצלחת להביא?
להגיד, אתה אומר משהו בתחילת המושב?
אני אמרתי.
איך זה עובד?
אני רק אומר שאנחנו מתחילים, ושאת תדברי ראשונה, אבל אני מעביר את זה לך, כי הוא אומר שצריך לדבר בתוך זה.
לא עם מצגת או משהו שכן.
לא, אני עם דף.
מראש, כמו פעם.
זה חיוך.
איזה אולד סקול.
זה חיוך. טוב, אנחנו רוצים להתחיל. אוקיי, אנחנו מתחילים, השעה 1:30, ונתחיל עם מעיין, אחת מתלמידותיו של מוטי, שעוד נשמע עליה בהמשך.
בעזרת השם. ועוד יגידו. טוב, אני כתבתי על דף הכי אולד סקול. יאיר ויוחנן, שומעים אותי? טוב, אז מוטי יקר, אני מאוד מאוד מתרגשת וזה כבוד ממש ממש גדול בשבילי לעמוד כאן, לדבר אליך, לדבר על כולכם ולברך אותך בשם הסטודנטים והסטודנטיות שלך בעבר, בהווה ובעתיד. אני רואה את זה כזכות אדירה לקבל את ההזדמנות הזאת, להודות לך. ביקשו ממני לדבר וישבתי וחשבתי על מה הייתי רוצה להודות לך, ואז חשבתי שהייתי שמחה גם להודות לאמוץ, אני לא יודעת אם הוא עדיין פה, אבל אמוץ באיזשהו שלב ככה סוג של אסף אותי, אמוץ עגנון, ואמר לי בואי תעשי מאסטר עם מוטי ובועז. אני זוכרת שנסענו בטנדר חזרה מבציידה או משהו, והוא אמר לי אם את תלכי על המאסטר הזה זה יהיה מה שנקרא הקרם דה לקרם של האקדמיה בארץ, והלכתי על זה. ומוטי הנחה אותי יחד עם בועז ואמוץ, וכשהכרנו רק בהתחלה היה לא קל, היה מאתגר, היה לנו לא קל להגיע למקום של אמון אחד בשנייה, ואנחנו טיפוסים מאוד שונים, שנינו מאוד דומיננטים, אבל אני זוכרת את הפעם הראשונה שאתה אמרת לי שאתה חושב שהעבודה שלי מצוינת, והייתי כל כך מופתעת, כי פתאום הבנתי כמה אתה מאמין בי וכמה אתה רואה את הפוטנציאל שלי הרבה יותר ממה שאני מסוגלת בכלל לראות. והיה לנו מאוד מאוד קשה לפרסם את המאמר מהמאסטר, אני אספר לכם. נפלנו על הריוויור על הפנים ומאוד מאוד מאתגר, ומוטי פשוט תמיד 100% מהזמן מאמין, אין דבר כזה שזה לא יתפרסם, אין דבר כזה שזה לא ילך. אני כבר הייתי בדוקטורט ו3 בלילה אני לא מצליחה להירדם כי המאמר לא מתפרסם ונורא נורא קשה, ואני מדברת איתו והוא לא מוותר ודוחף ואין לי כוח והוא עדיין דוחף ולא מוותר ולא מתייאש, והמאמר התפרסם, ומאמר לא רע יצא בסופו של דבר, לדעתי. ובכל אחד מהאתגרים האלה שנתקלנו בהם, תמיד, כל פעם שהייתי כזה אומרת, וואי, איך אני ממשיכה מפה, תמיד המסקנה הסופית שלי איתך, הייתה להבין כמה אהבה ונתינה אינסופית יש בכל, אבל בכל דבר שאתה עושה, בשביל הסטודנטים שלך, בטח ובטח כמובן, סטודנטים וסטודנטיות שלך ואנשים שאתה מנחה ואנשים שאתה עובד איתם. ואני אסיים עם אנקדוטה קטנה, או כמעט אסיים עם אנקדוטה קטנה, סליחה עדי. רגע אחד חזק שאני ממש זוכרת ממוטי זה לא בדיוק כשהתקבלתי לקולומביה, ללכת לעשות דוקטורט, אלא כמה ימים אחרי. הייתי בתקופה לא פשוטה בחיים, ופשוט כאילו, לא יודעת, כל כך לא הבנתי בכלל מה זה ללכת לדוקטורט בקולומביה, ושכחתי להודיע לו ולבועז שהתקבלתי. ומוטי התקשר אליי, לצרוח עליי, ואמר לי, יא מטומטמת, איזה הישג מטורף זה, איך את לא אומרת לי, איך את לא אומרת לנו, מה נסגר איתך, כאילו, איפה את חיה, באיזה סרט את חיה? רק אז קלטתי מה זה בעצם אומר, זה שהתקבלתי לעשות דוקטורט בקולומביה, ואני מאחלת לך מוטי, שתמשיך לצרוח על אנשים, תמשיך לצרוח על אנשים שסביבך, כמה הם נהדרים, וכמה הם טובים, וכמה הם לא צריכים לוותר, ותמשיך לדחוף אותם, כמו שאתה, הם לא יכולים בלעדיך, לא היינו מגיעים לאיפה שאנחנו בלעדיך. אני רוצה לעשות משהו קטן, אני מבקשת מכל הסטודנטים והסטודנטיות של מוטי לשעבר, אם לא אכפת לכם, אם אתם יכולים, תעמדו. תעמדו, אל תתביישו. ואני מבקשת מכל מי שנמצא בחדר הזה ושמוטי עשה בשבילו משהו שהוא רוצה להודות לו עליו, לעמוד. תעמדו. אם אפשר. אם אתם יכולים לעמוד, אם יש לכם כוח. ואני רוצה להגיד, אני בטוחה שלכל אחד ואחת ממי שנמצא בחדר הזה יש על מה להגיד תודה למוטי, אז אל תשכחו לעשות את זה, גם עכשיו בלב וגם באופן אישי. תודה.
גם יאיר אמר שהוא היה עומד, אבל הוא פשוט כבר מתכונן להרצאה שלו, ובאמת ייתן לנו את ההרצאה הראשונה בסשן, באיזה מידה ההולוקן הקדום יכול לנבא מה שצופה לנו העתיד הקרוב. אז יאיר, בבקשה.
I assume it's in English. I didn't prepare it in Hebrew. Is that okay? So anyway, thanks for inviting me. It's really, I'm really glad. I have never worked with Motti, nor published or collaborated, so I'm not sure what I'm doing here, but I have a lot of respect to Motti as a friend and as a scientist, so I'm more than pleased to share some of the work that I did, and I chose it because as soon as we published this paper in January, and that paper, the lead author is Sam Boba over here. You can see her carrying one of the long course from the ILDP expedition that we have actually in Chile in 2019. Steve Goldstein is over here. Anyway, and my collaborator Leo Zhenyu over here, Mian and Shtal that was in my lab. But Motti was one of the first to essentially cite it and believe in the record, which is a lot about it. So, as you know, if you look at the temperature record, and last week, of course, we talked a lot about that, the global temperature record. It's not very encouraging. We are at about exceeding 1 degree centigrade warming over the past 50 years, and just the recent AR6 of the IPCC that was published this summer, essentially talking about, ideally 2 degrees, but more likely 4 degrees, because I don't see right now cutting emission. So as paleoclimatologists, we often ask the question, can we use analog in the past when global temperature was a little warmer to essentially look at what a warmer climate can bring with in the future. And here is an example of a paper by Andrea Datta in 2015 trying to look at other warm interglacials. So the present you can see over here, this is an old paper, though of course it's not updated, but she's comparing it with other interglacial, namely the last interglacial stage, marine stage 5E that you see here. The temperature was about maybe 1 degree, 2 degrees warmer, depending on who you believe. And then you can look at the MIS 11 over here, about 425,000 years ago, and the Pliocene. I won't get to the details here. I don't think those are the best choices, but nonetheless, you know, the idea that she was asking essentially what would be the changes in global sea level, something that I worked, and I'm not going to talk about that right now, but still highly debatable. In terms of the local question, one of the questions that Motti, and I prefer myself to the talk here, you know, has been partially interested, of course, in the fate of the Dead Sea and essentially the evolution of the Dead Sea level, as we see here from the Reed Weber recent publication. Now, the Holocene is a unique among interglacial and something that attracted a lot of attention. I mean, the interglacial that I mentioned, the stage 5E, 9 and 11, which I think 9 is more important than 11, in this question, and all of them has an early interglacial warming. And the carbon dioxide and greenhouse gases recorded this time, they all show an early maximum and then a decrease thereafter. The Holocene is unique in the sense that what we see is actually low CO2 in the, and methane for this case in the early Holocene increasing toward the present. And I'm not talking here about the pre-industrial, post-industrial increase in greenhouse gases. Now, this has been a subject of debate, and what I'm showing you here at the top, we're showing a simulation of mean annual global temperature by the trace model over here, and the SST, the sea surface temperature, described as anomaly, and at the bottom we see the driver, namely the greenhouse gases, and here we have the carbon dioxide, methane, and nitrous oxide, all expressed as radiative forcing in red, and then in blue, two compilation of sea level during the Holocene, and I'm talking about the last 12,000 years. Now, all the models almost unanimously give consistent result, really showing the warming starting in the early Holocene and proceeding almost monotonically and progressively toward the pre-industrial period. And the explanation for this sort of linear warming is essentially that in the early Holocene we have essentially seen the effect of retreating ice sheets and reduce albedo, planetary albedo, whereas at the late Holocene, started at around 6,000 years ago, we see the effect of the increase in greenhouse gases. Just to look at those of you that don't know, we're talking about increase of about 3 parts per million in carbon dioxide, and then of course methane and nitrous oxide at the same time. So if we compare it now to the paleo record, so at the top of this panel, again, we're starting the Holocene, so the old is on the left and progressive to the present on the right. We see two compilations of proxies, both marine and terrestrial. Nielo is the Marco et al. 2013. And then later we have a more recent record that we have. Both of them showing very clearly about 0.5 degrees centigrade global warming relative in the early Holocene relative to the late Holocene. So if you compare it with the model results in blue under that, clearly you can see that there is discrepancy between those two records. So if you interpret, the proxy data as reflecting mean annual temperature and compare it with mean annual temperature simulation, there is a conundrum. And in 2014, we published the Holocene conundrum, but this has been known even before that. And the question came, and of course, a lot of the pundits jump and say, well, you know, if the models cannot simulate the Holocene, then they don't worth anything, and of course, we cannot trust it. The question for us as scientists was, you know, where is the culprit? Is that in the proxies that are very likely seasonally biased or spatially biased, or there are deficiency in model parameterization? It's important to say that I'm showing here only one model, which is a transient model, but we tested it on many, many models, and all of them are consistent. So, and those are fully blown models, and in fact, in the PIMP 4 that just came out with the IPCC, the discrepancy is even larger. So for more than a decade, we all knew that the discrepancy of the conundrum is not just between the model and the proxy, but also among the proxies. So here I'm showing records of temperature generated both by alkanon on the right and then by magnesium calcium. And they're both coming from in the East Equatorial Pacific. This is a region that climatically is very important, and it doesn't take much to show that essentially in cores that are not far apart, essentially each proxy is giving very different results. So which one you believe? Do you believe the alkanon that's showing a progressively warming during the Holocene consistent with the model, or if you are like me working with magnesium calcium, you say, well, no, actually there is a cooling. And this is almost globally, this is discrepancy. So you can't blame the models, and you are left with essentially the idea that proxy may reflect SST in different seasons. So we have a very strong seasonal bias, something again that we knew for more than 10 years. Nevertheless, most of the compilation essentially treating the data as reflecting mean annual temperature, mainly because we didn't know how to correct it. And if you look at modern results from sediment traps, and I know it's not very good record here, but you can see very clear that within a year, so 365 days, in different locations, all I want you to show that there are periods where we have much bigger floods of the foraminifera than other periods of the year. So even today, it's not a big secret that there is a seasonal bias in the bloom of foraminifera at the surface, and therefore they are seasonal, should be seasonally biased. So we wanted to test it, and this is something that I had in mind for 10 years. We had to look both at the right course and the right period. And what we did essentially, we chose a course that I collected in 2016 during the ILDP Expedition 363. The core comes from this region, actually very close to the shore north of the Yuan Peninsula terraces, which is, most of you know, that's where Moti started his paleoclimatic tour to the force, I would say. So this is tribute for him. The core is U1485. It's a very high sedimentation rate, although when I tell it to Moti and Steve, they always telling me that the Dead Sea is much higher sedimentation rate. Okay. Why did we choose it? We chose it for different reasons. One is far from the confounding effect of the high latitude ice, so either terrestrial land-based or marine sea ice. And therefore, it's more directly affected by changes in radiative forcing. In other words, it is affected by thermodynamic effect. It has today low seasonality, but one of the surprising, and I spend a lot of time working on cores there, that many of those cores still show the decrease of the thermal maximum during the early Holocene, followed by decrease in temperature, what in the past when we called the new glaciation. So that's what we did, and we focused on developing the method of this course. Now the problem is the low seasonality at the present, hard to test the seasonal bias on those records. So the course that I looked for many years and retrieved essentially has enough resolution to essentially resolve the last interglacial about 125,000 years ago. And the nice thing about the last interglacial is because of the high eccentricity, we actually have much higher seasonality. So what you see here is insolation in watts per meter square, and then you see the July and January insolation curve and the arrows that show you the degree of seasonality. And you can see that essentially during the last interglacial, which is our target, the seasonality is much higher than during the Holocene. So having this target, what we do is we generated an SST record from a surface foraminifera, the G Ruger that you have here. And so we have what we call the seasonal bias SST. And now we are comparing it with different insolation record for each month, okay? And one thing that I wanted to show you, the mean annual in magenta over here, you can see that the mean annual change is very small. It's about few watts per meter square, whereas the seasonal insolation are much higher. We're talking about several tenths of watts per meter square. So we basically try to find what we call the apparent season and compare it with what is the best fit to the seasonal insolation. Once we have that fit, we say, okay, that is the seasonal bias that we have toward in the SST record. So the next thing that we do essentially, once we know the seasonal bias, we take the difference or calculate the difference between the seasonal insolation and the mean annual. And you can see it's on the order of 40-50 watts per meter square, okay? We linearly correlate it with this difference in insolation, calculate the difference, expected difference in delta SST due to the radiating forcing of the insolation, and then correct the seasonal record. So here is your seasonal record, and here is after the transformation where we remove the seasonality from this record, and you can see that for the last interglacial, essentially, we're taking a record that looks with a thermal maximum and flattening it, essentially using this linear transformation. Now we can do the same thing, and we assume that the seasonality is the same. Those assumptions all needs to be a challenge, of course, and use this relationship and applying it to a seasonal difference in insolation for the Holocene. So here is the record for the Holocene. In this core, unlike other, for example, we don't have a strong seasonal decrease in the temperature, something that we see in other cores. But once we do the transformation, what you see here is essentially that the record is showing a slightly increased temperature, almost a 0.6, 0.7 degrees centigrade through the Holocene. Very different outcome than the assumed thermal maximum in the seasonally biased record. So the next thing, we were very, very selective in the record that we took, record where we have either alkinone or magnesium calcium, record where we have the last interglacial, so we can essentially use it to determine the apparent seasonality. And I call it apparent. We can't tell you if it's January or November, but we can say what's the bias to warm season or cold season in each of these proxies. And we can change the window, that won't matter, but all these scores between 40 north and 40 south, notice that they're biased to the northern hemisphere. We don't have enough record from the southern hemisphere, a caveat that we all have to deal with. We can generate a full stack between 40 north and 40 south. And again, the stack is over here, so 12 to 0 present on the right. So in the red, we have the seasonal bias. So that's the observation stacked statistically as we get them. And then using the transformation on each of these records and then compiling them into a stack, we get a stack essentially that looks very different. No more thermal maximum, but we have a progressive warming throughout from the early Holocene to the late Holocene. And of course, this is nothing compared with the recent warmings that we have from human activity. Now, interestingly enough, if we now compare it with the trace simulation, and we use two, the accelerated and the non-accelerated, you can see that essentially there is a very good consistency between the simulation other to the 40 south 40 north band all global over here between that and our record that we see here. So that kind of gives some confidence that the transformation has some merit. Now, I want to point out that the transformation was applied both to the real data, but also to the seasonal simulation in the model. So we tested it independently. We don't use the model. We just test the transformation on either model season or the data that we have here. If we now compare it essentially with a previous compilation that I show you, so here is the compilation as published by IPCC, and before it was the thermal maximum and so-called neoglacial cooling that you have over here. Again, everything is anomaly, so we're talking about few tenths of a degree, but for a stack is really important. And if you compare it with ours, essentially the stack as published previously is consistent with what we call the seasonal bias stack. Very, very different than what we see over here in the global, in the mean annual compilation. I already showed you that this is consistent with the trace simulation. If you, for example, compare it, and in this record in the light blue, you compare it with the trace result only for greenhouse gases, you see that it doesn't really, it's not fully consistent only in the late Holocene. And the reason is that in the early Holocene, as I show you, the dominant factor is the decreasing planetary albedo by the retreating ice sheets. Now we can ask the same question which I already started with is, how do we deal with the LIG, with the last interpolation, and compare it with the Holocene? So what I'm showing you here, and I'm almost at the end. On the right, we see the forcing in essentially radiative forcing, comparing the LIG with the Holocene. So much stronger seasonality we can see in the LIG. And as a result, of course, the seasonal bias, which we use as a target, is much higher in the SST. So here is the seasonal bias SST for the LIG compared with the Holocene. Apply this mean annual transformation, and we get for the LIG essentially a flat curve. Remember, the LIG has no change in the greenhouse gases during that period, as opposed to the Holocene, where the greenhouse gases are increasing in the late Holocene. So the Holocene is increasing, the LIG is flat. The LIG is few tenths of a degree warmer, so it is warmer than the Holocene of the pre-industrial. And that is consistent with what we know, essentially also on the sea level. By the early LIG, last interglacial, essentially sea level was already a few meters high, arguably, and all the ice sheet already retreated, so the effect is minimal, as opposed to the Holocene, where we still have until probably 5,000 years ago effect of the retreating ice. So to summarize two things, the question that I pose is, so is the early Holocene LIG good analogs for future global warming? If you trust our data, and I think motive to trust it, the answer would be no. And maybe for the LIG. But we really need to there are issues, and I can tell you there are a lot of things that we need to understand about our assumption. We also need an independent confirmation. Just last week there was a paper by the group from Arizona, Osman et al., that essentially used a completely different approach using Bayesian statistics to specially compile this data. Without getting into all the detail, I can tell you that their compilation is completely in agreement with us. So either we are both right or we are both wrong. Some things that I hope a lot of other scientists are going to test, including ourselves. I'm going to finish here, and I wish I was there, but you know, I thought, you know, in the marine environment, we always celebrate Neptune as the god of the sea. Here is every equator crossing, we have to celebrate it, and I thought I should celebrate and tell Motis that, you know, in paleoceanographic time scales, you're still very young, and I look forward to see more of your work. So, congratulations.
We have time for one or two quick questions. Moti, any questions? Okay. So, Yair, thank you very much. Please stay with us. אנחנו נעבור חזרה לעברית, והמרצה הבאה שלנו היא שקמה זערור, שתדבר על מה קורה. In English? Okay, so next speaker is Shikma Zarur, who is going to tell us a little bit about the dust in East Asia.
מורידה אותך למטה קוראים, כן?
כן. מה עושים פה? הנה, קוראים לידי טולשטיין. והוא מטפל בו.
ואתה תהיה אחראי על ההייטק.
למה? זה פתוח.
פשוט עשיתי לו מינימייז, לא, לזום, כן?
זה שלו?
זה לא.
יש לך את הצ'ופצ'יק הזה?
Okay. Thank you, everyone. Thank you for the organizers. Can you hear me in the back? Can you hear me in the back? They train us for geochemistry, not for this. Okay, thank you for the organizers, Mazal Tov Moti. I'm going to share with you work that I did with Moti and Yigal as part of my postdoc when I came back to Israel a few years ago. Regarding dust sources to marlakes in Eastern Asia as a way to look at changes in the East Asian monsoon. Okay, so the East Asian monsoon system is a very important and big climate system in East Asia. I'll do this. לחצתי פה על כמה, רגע, okay. So, I think mostly in the media we hear of the East Asian monsoon in terms of the summer monsoon, which is associated with very strong rains. It's like the rain season. But there's also the winter monsoon, which is the opposite wind direction. It's an opposite system with a high here that drives cold, dry air from inland outwards, and that's associated with big dust storms. And my talk is going to be focused mostly on this component. And some of the questions that we ask about the system is what drives the system, short-term, long-term, and how does it change over time in terms of the intensity, the geographical extent. Do the winds go further? Does the whole system extend really far south, or does it stop somewhere here? And how can we track these changes in the past? There have been many studies in this area. I'm just going to point to a couple very famous, well-known ones. So a lot of work has been done on the speleothems from caves here, where mostly, but not only, oxygen isotopes were measured. And you can see with the changes in the oxygen isotopes in the speleothems, changes that are related to the relative intensity of the summer and winter monsoon systems. These are mostly associated with the precession cycle, or the precession cycle tends to be very strong in these records. Another very famous record where a lot of different proxies have been studied on it is the Les record from the Chinese Les Plateau. And here in this picture you can mostly see different layers of Les versus soil. So if it's very wet and the summer monsoon is more intense, then soils develop on the Les, and when the winter monsoon is stronger relative to the summer monsoon, then we get the dust deposits without them turning into soils. So these records, a lot of the records that come from the Chinese Les Plateau are mostly associated, or the frequency that is finest there is the obliquity or the eccentricity cycles. In our work, we looked at two marlakes in East China. One is Shihang Longguan, and I hope that I'm pronouncing it correctly, in Hobuangyan in the south. And the idea of using Mar lakes is that we have very good control over the sediment sources. So the sediments they don't drain large rivers or anything. So anything that's collected in the lake can either come from the rim or with dust. So it's very confined. And also, given that these are volcanic craters, we know that the local material is volcanic basaltic in composition versus the dust in the area that is felsic in composition. So not only that we have a constraint on what can come into the lake, we have constraint over what we would expect to see as a chemical or mineralogical signatures of the sediment that goes in. In a very, very simplified way now, I'm just pointing out to the lakes again relative to the major systems here. So we have the summer trajectories, but those are mostly associated with the rains, so not very dust driving systems. And then we have the westerlies. They can move north and south over time. And then we have the winter monsoon component of the dry winds that come from inland outwards. So this is sort of our framework to work with. And I'm going to start with Huguangyan, and we're going to try to see, first we just want to see if it receives dust. I mean, it's pretty far away from the dust system. There have been some studies that argue that it does receive a lot of dust, and you can track it in the monsoon. Others kind of contradicted that. So that was the first thing. What does this record in terms of the dust? And if it does record, does it record the changes in the monsoon patterns? So we looked at different components in the lake chemistry and the sediments. One very basic one is to look at the CIA weathering index, how weathered the samples are, and the titanium content. And the idea is that when we take material and we start weathering it or leaching it, we get an enrichment in the insoluble elements. And titanium is such an element, similar with aluminum, which is what is the base of the CIA weathering index. What we find when we look at the sediments here in the black dots versus the basalt or the soils from the region and the paleosoils is that we see that the sediment is enriched in titanium. And that sort of indicates to us that if we take the basalt and we start weathering it and leaching all the soluble elements, we eventually get these sediments. If there was a big contribution of dust into the sediments coming from the less plateau or the deserts, we would expect to see a dilution in the titanium relative to what we find because the concentration of titanium in less is lower. So first indication is that if there is dust, it's not very dominant in the sediments. We also looked at the rare earth elements and chondrite normalized patterns here. We have sediment samples here in these light colored lines. We have the basalts. We have granitoids from the region, and you see that we mostly in this context look at the European anomaly. We said that there's the big European anomaly in the Cathasia granitoids. These are granitoids from the region. I'll show it in a map in a second. And the regional, the less in northern China. We see that the sediments, again, with the REs, don't really seem like they're very rich or have any imprint of dust. But then we look at the strontium neodymium isotopes, and then the picture becomes a little bit more complex. So I apologize, the y-axis title got cut off, but this is epsilon neodymium here, and strontium ratios here. What we find is that we have the volcanic material over here. This is the basalt, and these are some pyroclasts from the area. We have the soils that we collected from just outside the lake, right here. They plot in this region, and they're separated here by size. The smaller sizes here are the fine fractions of the soil versus the larger fractions of the soils. And the sediments sit somewhere in between here, but they seem to be connected to the fine fraction of the soils. So it seems that if anything comes from these soils into the sediments, it's the fine fraction, and we have to figure out, well, where are these granitic-like soils coming from? And that's where the geological map really comes in handy, and we find that on both sides of this volcanic field, there are granitoids and the field is covered. Well, you have the volcanic cones, but the field itself is covered with fluvial sediments that likely have a lot of significant material coming from these granitoids. And these granitoids sit in this isotopic field over here. To be fair, the less plateau or the less deposits in China also have similar composition, but considering the geographical relationship and the fact that we also have big grains in these soils that seem to be associated geochemically with the granitoids, this is probably the more likely source. So we do have dust, very small amount, but it's mostly associated with local soil contribution, local dust, rather than something large and regional. If we then take the strontium isotopes only, a much bigger data set than what we showed with the neodymium before, and plotted over time, and now we consider strontium input from the soils to the lake as local dust input, we see that we do see variation in the strontium isotope ratios here on the y-axis over time. And we find that we have more dust, which would imply drier conditions that can allow local dust into the lake. And that is associated with stronger winter monsoons. We know that from other records also, and here in the peak of the glacial. We also see that we have that associated with the Heinrich events, which are known to be drier. And wetter conditions are associated with lower strontium ratios, and that is because we don't have those granitic local soils contributing dust particles into the lake. So that was the lake down here, the South Lake. And what about this lake here? This lake here, Shihainlug 1, we know is on the path of the storms, of the dust storms. When you look at the core, you can see that there's a lamina of dust in there. And here, we ask a different question. We ask, now that, because we know a priori that there is dust there, we ask what are the dust sources, and do they change over time? And we have different potential sources, and I'm grouping the deserts into groups here, not everyone separately. So we have the western deserts, the northern deserts, and the central deserts. And that's how I'll refer to them in the next few slides. So I mentioned that we can look at the core and see that there's dust in the record. We can see the lamina, but we can also see it with the titanium, for example, like I showed in the other lake. So we have titanium concentrations here on the y-axis and the weathering index. And here you see that contrary to what we saw in the South Lake, there is a dilution here of the titanium concentration because of the significant dust input from the lake. So if we started with a local volcanic material and we weathered it, we would expect to see an enrichment in titanium like we see here. But because we see strong dilution, we can tell also chemically that there's large dust influx. We also see that in the rare earth elements. So here's the europium anomaly, and we see that correlates very nicely, sits very nicely with the LES versus the local volcanic material. So the sediments are definitely strongly influenced by dust. And as I mentioned before, we're interested in the sources. So we know that there's dust, but where is it coming from? And where it comes from tells us something about the synoptic conditions. What are the wind trajectories? Which systems are bringing this dust into the lake? To do that, we go again to the strontium and neodymium isotopes. So we have here strontium on the x-axis and epsilon neodymium on the y-axis. And this is a bit of a complex plot, so I'll walk you through it. We have the local volcanic material here. We have the lake sediments here, and we have the fields of the different deserts groups marked here in these gray circles or balloons. The soils that were collected from around the rim all fall somewhere between the local volcanic material and the sediments, but we know the sediments can't be a source to the soils. So there has to be some external source of a felsic composition that would drag this towards here. And it's very clear that the northern deserts are a significant source to these sediments, and it also makes sense if we go back to this map where the lake is just downwind of the northern deserts. But if we take a closer look, we can see that some of these samples, they have to be a mix with some other source. We can't explain everything by the northwestern deserts, northeastern deserts, sorry. So which desert is it? Depending on which it is, it tells us something about the weather conditions or the synoptic condition, that would bring the dust. So we look at a little bit at climatologies, and so we have the monthly climatologies. These are modern, these are not paleo, but it gives us some framework. If we look at the climatologies for January, April, and June, and so winter, spring, where most of the dust storms are, and already deep into the summer season, the rain season, and also the backwind trajectory. So we have the lake here, and this map shows the stronger the color, the more trajectories, the stronger the frequency of the trajectories from that location. We see that the central deserts, the winds do go through there, but the western deserts, there's no wind components that could actually bring dust from those deserts to this location, at least in modern times. So that helps us constrain some of the possibilities. And then we say that between the possibility of the western or central deserts, it's more likely that these anomalies in the dust contribution from, not just from the northern deserts, marked here in this triangle, those anomalies in the isotope composition come from the central deserts. To bring dust from the central deserts, we get it mostly in the spring or early summer. It would probably imply that we're looking at a long spring or a delay in the onset of the rains of the summer monsoon. Another possibility that I found in the literature is that it could be through El Nino conditions, but I didn't find anything too strongly around that. So the next thing to do is to see how these things change over time. So what we have here is time on the x-axis. Here we have the strontium and neodymium records, and we can see that there's this very strong, long, stable period here, and some periods that are more wiggly, that there's more changes. But I mostly want you to look at this plot here, which basically we calculated the fraction of contribution of dust from the northern lakes versus the central lakes. So 1 would mean that the dust that we see in the sediment sample is 100% from the northern lake, and anything less than 1 means that there is contribution from the central deserts. And when we look at that, we see that in this like more stable period, the baseline shifts down. If we compare to the baseline here, that is almost at 1, and it has strong but short excursions, here we just go down. There's a constant contribution of dust from the central deserts. Whereas before and after, the baseline is higher and we have short excursions. These don't correlate very well with any clear event like Heinrich events or any of those others, but this long period does somewhat correlate with leading to the glacial maximum and drier conditions. This could be, this was supposed to. It correlates with the leading towards the glacial maximum, and it could be that during this time, well, we know from other records that during this time the winter monsoon is stronger, and so it could be that not only that the monsoon is stronger, this whole period is affected by delays in the summer monsoon, and we get more dust from the central deserts. It changes the wind component. Then we have just for comparison, the oxygen record from Hulu Cave, and those shows, unlike this record that doesn't show any frequency that we can correlate with like regional or global drivers, with as I mentioned earlier, the oxygen 18 record has a strong precession signal and variation in the winter and summer monsoon strength. And then if we go back to the strontium record from Huguangyan, which was the South Lake, we see that there's a strong winter-summer monsoon signature with more and less dust, local dust according to drier or wetter conditions. But we don't see precession. We see more of an obliquity signal, despite the fact that we're in lower latitudes. To summarize our work, we use chemical and isotopic composition to identify and quantify lake sediment sources. For the South Lake, for Huguangyan, we found that there is dust, but it's most likely local, and the dust input correlates with drier conditions. So it's not that strontium per se is a proxy for climate, but in this case, we can use it as a proxy for the dust, which relates to climate. And then in the northern lake, we find that we do have changes in dust sources. It's mostly getting dust from the northern deserts, as we would expect, but there are some contributions from the central deserts, and these could indicate periods with stronger winter monsoons and delays in the summer monsoon rain. And in general, when we look not just at our records, at the isotope record and the many other records that were produced in this area, we see that each archive actually records different components of the monsoon, and we really need all of them together to get a global or regional understanding of how this thing works and to understand how things change locally depending on local conditions. And with that, I would like to thank you for your attention and for the invitation. This is from my PhD. I did one project with Motti on my PhD and Motti fishing for Melanopsis shells. And, and one more thing is if you mentioned EGU before at the break, then Motti encouraged me to give a humorous short talk. And thank you, Motti and Yigal, for showing me how even a speck of dust could have a whole world in it. So thank you.
Questions? So, our next speaker is Avi. He will tell us about the weather, or not weather.
Maybe weather.
Okay.
Okay. שומעים אותי מאחור? Can you hear me? Yes, no? Okay. So I'll be talking today about the question of was the last interglacial wetter or drier than today in our region? 1 second. And I want to begin with this well-known lake level curve of the Dead Sea. And I think we all recognize that the differences in elevation, the Holocene low levels and the glacial high levels, indicate to us wet glaciers and dry interglacials in our region. And this is sort of a common knowledge thing, at least in this room. And this observation or ideas were obviously confirmed with the deep drill of the Dead Sea. And you can see here the cycles of halite in gray in the Holocene, glacial mud and aragonite, wet conditions, high lake levels, the last dry interglacial, and so on and so on. And this is Motti holding the uppermost core that came out, the first section that came out of the core. And you can see this halite sequence, which is overlain by muddy water. But I'm not sure if many people in this room realize that if you ask 70, 80, 90% of the climate scientists in the world, they would all tell you that in the Middle East, the glacial is dry and the interglacial is wet. And this dissonance is well exemplified in these diagrams, these maps, which were published only 2 months ago by the IPCC, so supposedly state-of-the-art climate understanding of the world. Brown is drier conditions in the last glacial relative to today. And you can see Israel, the Levant here. This map indicates that the conditions were either slightly drier or just as wet as today. And when you look at the last interglacial, you can see this green blanket of wetness just covering the Sahara and in this case really penetrating well beyond Israel into the northern Levant. So there's what we thought was obvious in this community isn't necessarily so if you ask the global community. And the question remains, was the last interglacial wetter or drier than today? So the first thing I want to do is to dig in and look at regional archives. And this has been shown several times before, but I'm not sure everyone has seen this. So we can start by looking, first of all, at the Dead Sea, and the upper panel here shows in blue the lake level of the last, this is 200,000 years of time. In red, the sedimentary lithological facies reflecting low stands and high stands. And you can see this over time. I also plotted here the chlor-titanium ratios, which highlight in gray the timing of halite deposition. Now, at the same time, the Sorek cave and other caves like Peki'in and Tzalmon along these mountains, the Judea, Samaria, and Galilee mountains, show continuous deposition throughout these 200,000 years. So there had to be some continuous supply of rain during this time. However, if we move now to the rain shadow desert, looking now at the Ma'ale Ephraim cave in the Bik'ah and the Tzavoa cave in the northern Negev, and you can see the timing of deposition of these two caves, what we see is that this timing of deposition in the rain shadow is now more limited, focused on the glacial cycle. At the same time, these two caves, or this region, this rain shadow region, shows hiatuses, a lack of availability of water during interglacial times. Now, if we take this even further to the south, so now looking at caves in the Negev desert, travel times, and the references are here. Corals in the Red Sea, Boaz talked about that, and even fluvial deposits in the Sahara, and cave deposits and fluvial deposits along the Arabian Peninsula. What we see is that the timing of deposition or indication of wetness in these regions correspond to peak interglacial times, okay, marked here in red. So this diagram actually shows us that over this really short or small region, we have a switch in the climatic configuration between glacial and interglacial times. Glacials in the north are wet and interglacials are dry. In the south, glacials are dry, and we do see indication for wetness in the southern sector. Okay, so I think, to me, this is convincing. We do see some humidity penetrating or associated with the southern sector of the Levant during interglacials. But the question remains, was the Levant wetter or drier than today during the last interglacial? And does this, in fact, support this idea, globally accepted, that the monsoon really flushed the entire region with rain? So I'm going back now to the model that we saw in the beginning. And this is a model, to be more precise, it's a compilation, an ensemble of models, again, state-of-the-art coming out of the IPCC, of the percent of change in precipitation relative to pre-industrial times during stage 5e, the last interglacial. So really this is quite remarkable, and we can see here, just as an example, that in the middle of the Sahara, during the last interglacial, this model predicts more than 1,200% higher rain relative to present. In our region, this model predicts an increase, or more rain by 300%. Huge values, but remember that these are relative values, and if we actually move to the absolute values, okay, the absolute change in millimeters per day of precipitation, and if you squint and look at the region here at the Levant, you can barely see a green faint shadow. So whatever the rain that did exist or did precipitate at the time, it must have been really, really subtle. And if you look at the numbers, we're talking about 0.1, 0.2, 0.4 millimeters per day during summer alone. And this is a time which was much warmer than today. So even these amounts would be, in practice, smaller because of evaporation and the impact of heat. I want to acknowledge Yuda Enzel for pointing out this aspect of the global modeling. So monsoons don't seem to provide us with a solution, and this is despite the global or larger community sort of belief or understanding in this mechanism. The question is, because we did see indications of wetness, what are they associated with, and what are they about? So, an alternative mechanism that can provide humidity precipitation to the region exists today. And this alternative mechanism, we can see an example of that here. This is North Africa, and you can see this injection of humidity, this storm system, a tropical plume that injects humidity, precipitation all the way from the Atlantic Ocean to the Levant. And this, as I said, is known as a tropical plume. These events happen only a few times a year. Sometimes they don't happen in a given year. But during specific events, these tropical plumes can provide at least, if not more, the total annual amount of precipitation within only a few hours. Now, another mechanism that exists, which is similar to this, are Red Sea troughs penetrating from the Red Sea. And if we sort of compile everything together now, so it seems that based on the observations in Israel, in northern Israel and the Negev, that the Mediterranean cyclone systems during the last interglacials were essentially shut down. The best place to see this is in the Dead Sea, of course, low lake levels, massive halite deposition. I'm hoping I convinced you that the monsoon systems are really bad candidates to provide the or to be the source of formation of the observations I showed you associated with wetness in this region. But these, I would say, magical second-order systems, the tropical monsoons and the Red Sea troughs, can provide what we need. Now, so we have this evidence for humidity or wetness in the Levant during stage 5e. I just pointed out these mechanisms as being the source of this wetness, but it's sort of a magical solution, right? We don't know why would they suddenly take place during stage 5e. What is so special or odd about stage 5e that actually allows this to happen? It turns out that stage 5e is odd. In a larger scale of climate change, it is odd. And to explore this, I want to go back to the lake level curve. And what we can see here is the lake level curve over the last 70,000 years and the smoothed out or 3,000 years smoothing of the curve. So we see here, and this has been discussed for many years, close correlations between what this shows, which we believe to be regional hydrology, and global climate processes and parameters. The question is, which processes and which parameters are really the closest or the most controlling of this diagram. So to do this, we're looking now at a global map, looking at the Dead Sea levels. It's worthwhile testing the correlation between this lake level curve and as many archives as we can find. These can be nearby archives, even within the Dead Sea, lithology, the Sorek Cave, East Mediterranean records, caves near the Black Sea. We can even go further to Chinese caves, East Atlantic, sea level, Antarctic temperatures, and so on and so on. Now, when we test these correlations, so testing which of these records is most similar to the Dead Sea water levels, the results are presented here. I'm going to spare you all the nitty-bitty statistical examinations, but the y-axis is the R-square value. And what you can see here, these blue curves, are basically showing us that the global temperature record and the atmospheric CO2 are the two parameters which are most closely correlated to the Dead Sea water levels. Okay? So what?
Negatively.
Okay, negatively, but it doesn't matter. They're most strongly correlated to them. And this, first of all, is quite outstanding because you would think maybe East Mediterranean records, the Sorek Cave, closer records would be more similar. But it turns out that global temperatures are the first order controller of regional hydrology as far as we believe the Dead Sea lake level. Now this, I think, is quite important, but we can even take this a step further and use this correlation to extend the Levant hydrological record. And the way to do this, I'll show it now. So we're looking now at 200,000 years of a Dead Sea water budget. In the upper panel, the lake level again, okay? So this is Lake Lisan, high glacial, low Holocene, and the reconstruction of a relative lake level coming out of Waldman et al. Again, the lithological facies showing low and high relative lake levels, and chlorotitanium highlighting the timing of deposition of halite sequences. Now, if I plot the Antarctic temperatures reversed over the lake level, so we have warm temperatures in the Holocene, cool temperatures in the glacial, and so on and so on. First of all, we see a really nice fit here, and places which don't show an exact fit are actually quite interesting. I won't go into that, but these offsets are telling us something that is important and we didn't actually know before. I won't go into that, but we can go back in time and see the predicted low lake level in stage 5e, and so on and so on. Now, we also know that this extremely low lake level, or synthetic low lake level, seems to be an excursion. If we plot this orange line here, which goes between the extreme or the maximum extent of the Holocene and other interglacials, we can see that clearly stage 5e, the peak of stage 5e, crosses some threshold, in this case a threshold of temperature, which is odd because we know that in our region, this is exactly when we find this, as I said, odd behavior, these penetrations of humidity from the south, this sudden, I would say, magical occurrence of tropical plumes. But again, if we look at this, so this is the excursion of the synthetic predicted lake level, and mimicking this excursion now into the lithological record, we see that instead of reaching a really low lake level or relative lake level here, this wetness actually pushes up the relative lake level. So what we find here is that crossing the threshold in our region within the Dead Sea watershed actually switches the synthetic correlation between the Dead Sea or regional climate and global temperatures. So in fact, rather than reaching a really, really low lake level, what we find is that the threshold crossing actually provides us with a slight increase in water levels. It's only slight, okay? We know that everything is fairly dry, even though we have these slight indicators of wetness. Now, based on this understanding and the really strong correlation between Dead Sea water levels and global temperatures, we can actually extend now this record back in time and establish a synthetic regional hydrological archive, which is plotted here. And what we see here is the lake level in blue, okay, which only extends back to 70,000 years, but we can take this further back in time all the way to 800,000 years, and this is assuming the connection that exists today, whether we understand what's behind it or not. If we assume this connection existed back in time, at least into the Middle Holocene, we have this synthetic hydrological record, which also takes into account the clipping, the cutoffs during peak warm phases during interglacials. So to sum up, and to answer the question in the title, the answer is a bit complex, right? So the last interglacial in the Levant was, I would say, extremely hyperarid in the northern sector, but we do identify wet conditions, slight wet conditions in the southern sector. And despite the intensification of the African monsoon at the time, it's hard to think or hard to believe that the African monsoon actually penetrated all the way and was the cause, was the trigger to the wetness we see in the Levant. Rather, what I'm suggesting here, and other colleagues have suggested the same, is that we're looking at an incursion of almost violent events, tropical plumes, triggered by a crossing of global temperature threshold. Based on the correlation between temperatures and regional hydrology, we can establish a synthetic lake level curve which can be used for various other studies of regional hydrology. And finally, the final take-home message is that based on these observations, in a warmer world, whether it's stage 5e, the last interglacial, or the coming century, based on this study, what we would expect is an increase in the frequency and intensity of extreme weather events in the southern Levant. So I want to leave you with this sunset, a picture of the sunset in the Red Sea, which Moti doesn't remember, but he took it. So, toda rabba.
Thank you, Adi. And our next speaker is Yohanan. So you should put in זה מוקלט או שזה...
הכל מוקלט.
מוקלט?
כן, כן. יוחנן? רגע. יוחנן?
אני פה.
אוקיי.
רוצה לדבר איתו?
Okay, Yohanan, I hope you're ready. So, without any further ado, Yohanan, the stage is yours.
Thank you. So I have this fancy title that how Moti introduced me to a journey into the past, showing me the Dead Sea time machine. So first of all, happy birthday, Moti. Thank you all, Adi and all, for the invitation to participate in this workshop. It's an honor and a pleasure. And I'm sorry I'm going to miss the real party. Is there one after this? I'm not sure, but if there is, I'll miss it. So I will tell you a story in two parts, essentially covering two papers that we published together. One of them is, the first one is the Holocene Dead Sea level variability and how it's connected remotely to global events in the North Atlantic, my favorite part of the globe. In 2007, Moti showed me this time series of the Dead Sea, and you've all seen it. And he said, okay, let's explain what's happening, what's that variability. And he essentially meant the centennial to millennial type variability that happens during the Holocene, the Dead Sea level variations. So we both actually looked at a paper that Yehuda Enzel already published with other colleagues in 2003, and he said Jerusalem is rainfall record is the key to what's happening in the Middle East today. It's a long record that starts in 1846 or something like that. And we took Yehuda up on this word, and we said, let's look at the correlation between Jerusalem and annual rainfall everywhere else. And this is the map that jumped in front of us, and it shows this anti-correlation with the monsoon region, summer monsoon region in North Africa, all the way to North America, which is bizarre. And actually, I used the additional information on North American rainfall from 3 weeks that Ed Cook published in a atlas of North American hydroclimate. And that verifies too that interesting correlation, especially with the western US. So what's controlling this thing, especially what's the anti-correlation between Jerusalem and Africa when these things happen in different seasons? Africa gets its rain in the summer and Israel gets its rain in the winter. And the only explanation that we could come up with is that it's the Atlantic Ocean which is in the middle of all of this, and its variability, which is known as the Atlantic multidecadal oscillation. It's long variability, not its interannual variability. On the left here, you can see a figure which shows the Jerusalem rainfall record from 1846 to, at that time, I only had data till 1996 or something like that. And the bars show the annual rainfall, and the red curve in the upper diagram on the left shows a smooth version of that rainfall series. The blue is the time series of the Atlantic multidecadal variability or oscillation. You can call it in any of those names, it will be well recognized everywhere. And below is the correlation between Jerusalem rainfall and sea surface temperatures in the northern hemisphere and the tropics, and it shows a negative correlation with specifically the tropical part, or the subtropical and tropical part of the North Atlantic, is sort of resembling vaguely the pattern of the Atlantic multidecadal variability. The Atlantic multidecadal variability index, to remind you, is the average of the sea surface temperatures from the equator all the way to the tip of Greenland. On the right side here, you can see 2 or 3 actually paleoclimatological archives of the last 3,500 years. The top one is the bond cycle of, forget the exact word, but it's the hematite deposits in the bottom of the North Atlantic. The second diagram is sea surface temperatures reconstructed from forums in not Bermuda, but in the middle of subtropical Atlantic by Caidwin et al. In 1996. The Dead Sea curve appears in the third diagram, the second from the bottom, and below is the record of glacier spreading in the Alps. So the Dead Sea curve appears in the middle between indicators of the Atlantic temperature, and you can see the indication in the Sargasso Sea diagram that Caidwin put together. Negative SSTs are on the top and positive SSTs are on the bottom. In the bond diagram, high levels of hematite grains indicate incursion of glaciers from the Greenland Sea into Iceland and to the south of it. And the spreading of the glaciers also indicates winter cooling of Europe, which is possibly or quite certainly affected by the temperature in the North Atlantic. So that sea level goes up, seems like every time it's cold in the Atlantic. So it verifies the observed record in the left side. The most recent reconstruction of the Dead Sea puts a few changes in the Dead Sea levels in the recent past, but it doesn't break up that relationship between the North Atlantic and the Middle East or the East Mediterranean. So is that also something that we can recognize if we look at the entire trend over the Holocene of the Dead Sea levels? The diagram of the Dead Sea level shows here that the level of the Dead Sea increased between the early beginning of the Holocene and the middle Holocene. At the same time, the lakes in Africa declined, as you can see in the lake level curve. And it's also the same time that the insolation, summer insolation went down over the northern hemisphere. And Alkedon data reconstructed all the way on the right also shows that the North Atlantic seemed to cool according to Alkedon measurements during that time. So now we go to the present reconstruction, which is from Weber et al., and it actually doesn't show this rise in Dead Sea levels that we saw in the previous record. So the correction based on the Cape Cavan or in-Cavan reconstruction actually changes the lake level record, and it shows a gradual, if you look at the troughs of these curves, it shows a gradual decline, and Yair already mentioned that in his talk. So going back to what Yair said, the reconstruction of the temperatures that we are used to from the North Atlantic needs to be corrected based on the fact that it's seasonal. So it actually shows that the Holocene at least in the area that includes the tropical Atlantic as well as the tropical Pacific, has increased with time rather than had showed a peak in the early or middle Holocene and then decline. And Yair explained it, so I don't need to go into it, why that is. This is a curve taken from a paper, recent paper by Logo et al., which talks about Alaska, not the Middle East, but it does show the summer insolation curve, the winter insolation curve, and the rise in greenhouse gases that Yair also mentioned. So we have to actually digest this new data. And I think Moti and I were talking about this and trying to understand exactly what governs the long-term trend in the Holocene. But I think that the millennial and centennial variability is pretty well connected to the cooling and warming of the North Atlantic on that time scale. So the second story is the story of more recent story about the effect of solar variability. And I don't know if I have too much time to get into it, but I'll go very quickly about it. So I think it was in a visit to, 3 months visit to Jerusalem that I had way back before 2019 for sure, because the paper came out in 2019. But that showed, Moti showed me a discussion at that time, a draft that the late Ronnie Ellenblum was working on, which talked about the very extreme state of climate in the early medieval period in the Eastern Mediterranean. And it was a story of Nile Valley drought that happened in very synchronous way with cooling in Central Asia, with invasion of nomadic tribes into the Middle East, all a story of very cold Middle East and very dry Egypt at the same time during the middle of the 10th and up to the middle of the 11th century, early medieval. So it was Moti that suggested, okay, what happened at that time? And he was mentioning a solar minimum, a grand solar minimum called the Oort minimum, that showed the decline of the solar energy, the irradiance of the sun in that part of the early medieval. And we looked at, that's shown in the diagram above. It shows 3 curves based on beryllium-10 and 3 carbon-14 constructions. And it shows a decline in insolation, a very small decline. Why would it matter? Well, there is some relationship in the early medieval between the levels of the Niles, which are shown below. The solid curve is the low pass part of the Nile variability, and the bars are the number of Nile dry events in a decade. And of course, those two are based on the same data set, so there is an agreement between the two, between the bars and the smooth curve. The brown reddish boxes or squares in the same diagram are the severe dry event that Ronnie Ellenblum mentions in his book. And the blue diagonals are the cooling events in Mesopotamia from records of the historical records of the time. So it shows that very interesting possible correlation between solar minimum, low levels of the Nile, and cooling events in the Middle East. And I would like to mention here that the association between grand solar minima and Dead Sea drying was studied in Neugebauer et al. In 2015 in a paper, and was recently mentioned by Weber et al. In 2021. So what happens in the Dead Sea level curve? So of course it's a much coarser time series,
with a much lower resolution. And it does show, though, that around 1,000 years ago, the Dead Sea levels were really low. This was corrected from a previous curve by Stern et al. And also is shown in Weber et al. That the Dead Sea levels actually dropped to quite low levels at the early medieval period. So I'm masking that. We also looked at the Delta 18 records from Foraminifera in close to the Ashkelon area, and the Delta 18 levels in the Sorek Cave. And they both show a decline in Delta 18 around the same time. Of course, the resolution and the error in these measurements allows me to say that it's about the same time that the Dead Sea declined. And that agrees with this idea that it was cold and dry also in the Levant at the same time. So what is happening in general? What do we know about the relationship between solar variability and climate? This is a model run that was done by Neil et al. At NCAR, and it was published in Science in 2009, which shows a tendency for getting La Niñas during solar maxima, which in reverse would mean El Niños during solar minima. So a peak solar radiance gives you a La Niña, a minimum solar irradiance gives you El Niño on the 11-year solar cycle. So we would assume that a similar thing happens during the grand solar minima. Another paper was published in 2010 by Woolings I think it was at Reading at that time, shows a composite of the climate in Eurasia, in Europe and Asia and in Greenland during solar minima compared to what the usual North Atlantic Oscillation is doing to Europe. The North Atlantic Oscillation here is in a negative phase, high pressure over Iceland and low pressure over the Azores. So it's a negative North Atlantic Oscillation. We know it brings cooling to Europe, but Woolings claims that during solar minima, that minimum of Europe is much stronger and extends over Central Asia, and it signifies an increase in the intensity of the Siberian high. About El Nino, we know these records from Calcaya and from Cariaco, and they all seem to show indication of cooling of warming of the equatorial Pacific during El Niños. It shows as a decline in the titanium record in Cariaco, and it shows as a decline in Delta 18 in the Calcaya ice core. I'm not going to go too much into this, but this shows that almost in all the cases of solar minima, there is a tendency for the eastern equatorial Pacific to warm up like an El Nino, or have more El Ninos at the same time. And in the North Atlantic, we see from the geological record indications from reconstructions of temperature around Iceland that in the medieval warm period, in the old minimum, early medieval warm period, and then in the Wolf minimum's case, there is a tendency for temperatures to to cool in solar minima. Cooling is up, warming is down in this diagram. So we came up with this model of the solar minimum causing Siberian high case, stronger Siberian high, and as we know, in a strong Siberian high case, what is blocked is the formation of cyclones around Cyprus, and so we get cold winters in Asia and blocking of rainfall into the Levant. At the same time, solar minima cause El Niños, which cause a weak African monsoon, and then you have low Nile floods and droughts in Egypt. Anyway, these short stories show that the Middle East is connected very well to events in the global climate, as previous speakers have already described. And, you know, the journey with Moti still continues, and I hope to visit Jerusalem in the winter and spend some time there and learn more from my colleagues and talk more with Motis, and maybe something positive will come out of it again. Moti always followed the hypothesis that what's happening in the Dead Sea is connected to what's happening worldwide. And he never relentless, as Mayan already described at the meeting of this session, relentless pursuit of this idea. And I've learned a lot from him, and I thank him very much for that. And to be continued. Thank you all for listening. I hope I didn't go beyond time. Thank you.
Okay.
I know that
the end, and now we have
no, it's not the end.
Remarks.
Moti, if you didn't pay attention, wait quietly the whole day. He didn't say I have to say something.
לא הלכתי לשירותים.
So we're gonna give him 5 minutes.
עדי, בוא תחבר אותי רגע.
And meanwhile, I will open some bottles of wine, but we need to make a toast. הוא יעבור ביעף, אל תדאגו.
זה 5 דקות.
5 דקות.
מה אותי פותח? מה?
סודר. אפשר להוריד את זה. תן לי קודם לשים את זה. לא.
מתחת לראש.
טוב, יהיה עכשיו מצגת קצרה של 4 דקות שאני הכנתי במקום לדבר כל מיני דברים. אז אני אראה מצגת של 4 דקות, 4.5 דקות. אבל אני בכל זאת רוצה להגיד תודה, ואני רוצה שתמחאו כפיים לעדי טורשטיין ויעל עבר, שבאמת תרחו, ובאמת למרות שמררתי להם את החיים הרבה שנים, אז תרחו ועשו ויזמו ורצו וביקשו ונדנדו, ובאמת הרימו את כל ההופעה הזאת.
רגע, זה לא היה לבד, יש פה עוד צוות, יש פה את קרן שושנה ואת אלנה ואת יוסי.
זה בכלל הקרן, זה אני לא יודע. אוקיי, אני יכול להתחיל? וגם תודה רבה לכל מי שטרח ובא ונשאר כאן עד הסוף. אז רק, איך אני מעביר את השקופיות? אני מעביר אותם כאן.
מוטי, הילדים שלך, זה שכל היום...
וגם הילדים שלי באו...
מקשיבים פה מהבוקר.
והתלוננו שהם לא מבינים מה שאנחנו אומרים. אוקיי.
יש ערימה של חבר'ה על הדשא, אני דברים כאלה מחבר, בנים בנות ביחד, זה יפה שיש אומץ לי לפעמים להתערבר, שרים שירים ירח מסתבר, חושבים במי להתערב הלילה, אם כי הוא כזה קצת מעצבן. מתחת לראשי מונחת ירק, ועל בטני טלטלים מוטל, בלט יוצאות ידיים אל הדרך, ומסלולה ארוך ומפותח. קוראים נשים ומקשיבים לקשר, עינינו מתפתלות לחשושיות, יש הסתננויות בתוך העשר, כי יש בו כל מיני גבשושיות. כיוון שתרדמה עליי נופלת, שוב אין אני מצליח לרתר של מי היה אשר עליי זוכרת את גופי. ומה? וכשאני מקיץ אין איש בדשא, רק קצת קריר וקצת רטוב מטעם, ולהפתעתי אני רואה שאותו צרור טלטלים עליי מותר. ומתוכו אליי צוחקות עיניי, ומתוכו אליי מבהיק צוואר. אני שואל, היי מה הענייניי? היא בחיוך עונה לי, שואל גם את ישר, עונה לאו דווקא, ותשובתה אותי קצת מביכה.
שואל אז מה בעצם את עושה כאן? שפתיה לא חשוב, אני איתך.
אני שותק שפתיים, היא נושכת. אני שותק בחום כבדות ידיים, פתאום היא מסתובבת ורק אני שותק עוד שם.
וכולם ביחד.
תודה רבה.
אני דברים כאלה מחבר, בנים בנות ביחד זה יפה שם.
שטיין, לאן זרקת?
יוסי, אני משאיר פה את הפוינטר של הרגע. לא אמור להיות פה קבוע? לא, אז יש אחד קבוע ויש אחד שלו שנתנה לי זה. אתה יודע להחזיר לה או שנשאיר את זה פה? מה שאתה בטוח שזה שלו? זה מה שהיה כאן, זה באמצע הבילי, זה
חבר'ה, לא לשים אצבעות, אליסה, אצבעות לא נתנו. אליסה, מה זה צריך להיות?
אני בכל זאת אתעכב עוד איזה שעה אצל אמא שלי או משהו ש...
אין בעיה.
כן.
אנחנו ילדים גדולים, ככה אומרים. לא, ברור.
אבל האוויר הבצוקים הלך עליה.
אז תמיד יש בבירורה, אתה יודע.
כן.
ראית איזה תמונה שלך הבאתי? ראית מה זה? מה? זה תמונה היסטורית.
תשלח.
אני אשלח לך. אני אעביר את זה, כן. זה לא שלי.
שלא יצאו אותנו עכשיו ב...
רגע. הופ. טוב, ביי יוני.
טוב. אני אמרתי לך שקיבלו את מעמד טוריום?
כן, אני יודע, כן.
זה אירוע היסטורי.
טוב.
תודה רבה. גם יצא בצלח. באו הרבה אנשים. ביי, החברים, בני כמה אתם בכלל שאתם מדברים?
זהו, הייתי, פנו אליי כבר, חסר להם סן פרנסיסקו שנה הבאה,
הנה, שישלחו הצעות. יופי, כל הכבוד.
מה שמדהים בחולצה הזאת שהוא הסכים ללבוש חולצה שכמעט בו זמנית לתמונה. שזה מדהים, היום אתה לא תסכים ללבוש חולצה של 21. זאת התאביקה. מה הם אוכלים?
אתה לא בפייסבוק בעיה.
יש כזה דבר?
פעם בשבוע, אני כבר לא בגמרא. בסדר, כאילו יותר נכנסה לחברתי, שזה גם חשוב. אני הייתה מגיעה לכנסת, במובן הלאה,
אם הם עושים את זה בכיף, סבבה, כאילו...